high above the Arctic Circle. Curtains of green light ripple across the star-filled darkness, like silk scarves dancing in a cosmic breeze. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. CTA like and subscribe card. Luminous green curtains of light flowing across a star-filled Arctic sky. The aurora shimmering like ethereal silk against the deep black void. This is the Aurora Borealis, the northern lights, one of Earth's most beautiful displays of the invisible forces that connect our planet to the sun. A vast dome of night sky stretching over snow-covered Arctic wilderness. Brilliant green aurora dancing in vertical columns above the frozen landscape. The aurora appears roughly 60 to 400 miles above our heads, floating in the thin upper atmosphere where space begins to touch our world. Glowing green and blue aurora, ribbons weaving through the darkness, their light reflecting off pristine white snow fields far below. These lights stretch across thousands of miles, forming a glowing oval that circles the magnetic North Pole like a crown of fire. A massive oval ring of aurora light encircling the Arctic from high above. The green glow forming a perfect crown around the white polar ice cap. The aurora happens when tiny particles from the sun crash into the gases that surround our planet. Brilliant streams of green and blue light cascading downward like a waterfall of pure energy, illuminating the edge of space. These solar particles travel 93 million miles through the cold emptiness of space, riding invisible magnetic highways that lead them straight to Earth's poles. Shimmering curtains of aurora light rippling and folding like cosmic fabric. The green glow pulsing gently against the star-scattered darkness. When they arrive, they paint the night sky with colors that seem almost too beautiful to be real. Towering columns of green aurora light reaching upward like luminous pillars, their bases touching the horizon while their tops fade into the star-filled void. The northern lights appear most often in a ring-shaped zone that scientists call the auroral oval. This invisible circle sits about 1,500 miles from the magnetic North Pole, passing through northern Alaska, northern Canada, southern Greenland, northern Scandinavia, and northern Siberia. A panoramic view of the auroral oval from space, showing the glowing green ring of light encircling the Arctic regions of Earth. Delicate wisps of green aurora light drifting across the sky like luminous smoke. Their gentle glow contrasting with the sharp brightness of distant stars. People living within this magical zone might see the aurora 200 nights each year when the sky is dark and clear. Brilliant green aurora sheets spreading across the entire sky like a glowing ceiling. The light dancing and shifting in slow, hypnotic waves. The lights move constantly, sometimes slowly like drifting clouds, sometimes quickly like flames flickering in the wind. Rapid pulses of green and blue aurora light flashing across the sky in quick bursts, creating a cosmic light show against the Arctic night. Soft green aurora glow illuminating low-hanging clouds from above. The ethereal light creating a dreamy, otherworldly atmosphere over the frozen tundra. The aurora connects our small blue planet to the vast energy of our nearest star, creating a bridge of light between Earth and Sun that reminds us how everything in the universe flows together in perfect harmony. Majestic aurora, curtains hanging like cosmic drapes across the night sky, their green light shimmering with an inner fire that seems to breathe with life. Each photon of aurora light began its journey in the nuclear furnace of the sun, traveled through the void of space, and ended its path by creating this gentle glow that has amazed humans for thousands of years. Gentle waves of green aurora light rolling across the sky like ocean swells. Their smooth motion creating a sense of peaceful rhythm in the Arctic night. Brilliant aurora light painting the entire northern horizon in shades of green and blue. The glow reflecting off ice crystals in the frigid air. Tonight, somewhere above the Arctic Circle, the aurora is dancing once again, weaving light and magnetism into a display that connects the smallest atoms in our atmosphere to the largest forces in our solar system. Ethereal green aurora streamers flowing upward like luminous rivers, their light creating pathways of beauty between the earth and the infinite darkness of space. The solar wind begins its story 93 million miles away from Earth, in the corona of our sun. The blazing corona of the sun, extending millions of miles into space, its plasma tendrils glowing white-hot against the deep black of the void. This outer layer of our star burns at temperatures reaching 2 million degrees Fahrenheit. The heat is so intense that hydrogen atoms break apart completely, creating a soup of charged particles called plasma. Streams of golden plasma flowing outward from the sun's surface. The charged particles creating luminous rivers that stretch across the darkness of space. These particles cannot stay bound to the sun at such extreme temperatures. The solar wind races away from the sun at speeds between 200 and 500 miles per second. Invisible streams of solar particles rushing through the emptiness between planets, their paths creating ghostly highways of energy across the solar system. To picture this speed, imagine a particle leaving the sun and reaching Earth in just 3 to 4 days. The wind carries about 1 billion particles in every cubic inch of space near Earth. The Earth floating like a blue marble in the path of the solar wind, its magnetic field creating an invisible barrier around the planet. This might sound crowded, but space is so vast that the solar wind is actually thinner than the best vacuum we can create in laboratories on Earth. The particles in the solar wind are mostly protons and electrons, countless tiny particles of light streaming through the cosmic void, each one carrying electric charge and magnetic energy from the sun. Protons carry a positive electric charge, while electrons carry a negative charge. When these charged particles move through space, they create their own magnetic field that travels with them. Waves of magnetic energy rippling through space like invisible ocean currents, carrying the sun's influence to the edges of the solar system. This magnetic field embedded in the solar wind becomes when it encounters Earth. Our planet sits directly in the path of this constant stream. The solar wind approaching Earth like a gentle cosmic breeze, its invisible particles carrying the energy and magnetism of our nearest star. every second, about 6 billion particles from the solar wind strike the outer edges of Earth's magnetic field. The collision happens about 40,000 miles above our heads, in a region where space begins to blend with the very top of our atmosphere, the boundary where Earth's magnetic field meets the solar wind, creating a shimmering interface of energy high above the planet's surface. The solar wind never stops, an endless river of solar particles flowing past Earth day and night, the stream continuing its journey toward the outer planets and beyond. It has been blowing steadily for billions of years, ever since our sun first ignited its nuclear fires. The wind will continue flowing for billions more years until our star finally exhausts its fuel. The vast emptiness between Earth and Sun, filled with the invisible presence of solar particles, each one a messenger carrying news from our star. During quiet periods, the solar wind maintains a gentle, steady pace. But when the sun becomes active with solar flares and coronal mass ejections, the wind can surge to incredible speeds. These surges create the most spectacular aurora displays, massive waves of enhanced solar wind racing toward Earth, their increased energy promising brilliant light shows in the polar skies. A single coronal mass ejection can hurl billions of tons of solar material into space at speeds up to 5 million miles per hour, a colossal bubble of solar plasma expanding through space, its magnetic field lines twisted and compressed like a cosmic spring ready to release. When this enhanced solar wind reaches Earth, it carries enough energy to power the entire United States for millions of years. The journey from Sun to Earth takes the solar wind through a region of space that seems empty, but pulses with invisible activity. The space between Earth and Sun shimmering with magnetic field lines and particle streams, creating an invisible web of energy connecting our planet to its star. Radio telescopes can detect the solar wind as it travels, picking up the electromagnetic signals created by moving charged particles. Ghostly radio waves emanating from the solar wind as it flows through space, carrying information about conditions near the sun. Scientists use these signals to predict when enhanced solar wind will arrive at Earth, giving us advance warning of incoming aurora activity. The temperature of the solar wind drops as it travels away from the sun. Solar wind particles cooling as they journey through the frigid vacuum of space, their heat gradually dissipating into the cosmic void. By the time the particles reach Earth, they have cooled to about 100,000 degrees Fahrenheit. This might sound hot, but it represents a dramatic cooling from their origin temperature of 2 million degrees. The solar wind spreading out like an expanding sphere as it moves away from the sun, its density decreasing, but its influence reaching across billions of miles. The particles spread out over an increasingly large area as they travel, which explains why the solar wind becomes less dense with distance. Earth receives only a tiny fraction of the total solar wind that flows from our sun. The solar wind streaming past Earth and continuing its journey toward the outer planets, most of its particles never interacting with our world. The vast majority of solar wind particles flow around our planet's magnetic field and continue toward the outer edges of the solar system. Streams of solar particles flowing around Earth's magnetic barrier, like water around a stone in a river, most continuing their cosmic journey undisturbed. Only a small percentage of the solar wind actually interacts with our planet's magnetic field to create the aurora, the delicate dance between solar wind and Earth's magnetosphere, beginning high above the atmosphere, where invisible forces shape the destiny of charged particles. This interaction represents one of the most beautiful examples of how cosmic forces work together to create the natural wonders we see in our night sky. The story of the aurora begins 4.5 billion years ago, when our planet was still forming from the cosmic dust and debris that swirled around our young sun. A molten Earth spinning in the darkness of early space, its surface glowing red-hot with volcanic activity. No atmosphere yet protecting its burning landscape. In those ancient days, Earth had no magnetic field to speak of. The solar wind struck our planet directly, stripping away any early atmosphere that might have formed. streams of solar particles bombarding the early Earth's surface, the planet defenseless against the cosmic radiation flowing from the sun. Our world needed protection, and that protection would come from deep within the planet itself. As Earth cooled and solidified, something remarkable began happening in its core. The Earth's molten iron core beginning to churn and flow. Currents of liquid metal, creating the first stirrings of a planetary magnetic field. The iron-rich core started to convect, with hot liquid metal rising toward the surface, while cooler metal sank toward the center. This movement created electric currents, and electric currents generate magnetic fields. Invisible magnetic field lines beginning to emerge from Earth's core, reaching upward through the mantle and crust towards space. The process took millions of years, but gradually our planet developed the magnetic shield that would make the aurora possible. Earth's magnetic field works like an enormous bar magnet, with field lines that emerge from the magnetic South Pole and curve around the planet to enter at the magnetic North Pole. Earth's magnetic field lines flowing in graceful arcs from pole to pole, creating an invisible protective bubble around the planet. These field lines extend far into space, creating what scientists call the magnetosphere. The magnetosphere acts like a cosmic deflector shield, pushing most of the solar wind around our planet, rather than letting it strike the surface directly. The magnetosphere, stretching tens of thousands of miles into space, its invisible boundaries marking where Earth's influence meets the solar wind. Without this magnetic protection, Earth would be a barren world like Mars, which lost most of its magnetic field billions of years ago. The magnetosphere is not perfectly spherical. Earth's magnetosphere compressed on the side facing the sun. Its magnetic field lines squeezed together by the constant pressure of solar wind. The solar wind compresses the magnetic field on the day side of Earth, squashing it down to about 6 to 10 Earth radii from our planet's center. On the night side, the magnetic field stretches out into a long tail that extends far beyond the moon's orbit. The magnetosphere's tail stretching hundreds of thousands of miles behind Earth, like a cosmic wind sock blown by the solar breeze. This asymmetrical shape creates the conditions necessary for the aurora to form. The key to aurora formation lies in what happens at the boundaries of the magnetosphere. Solar wind particles pressing against the magnetosphere's outer edge, some finding tiny gaps where they can slip through Earth's magnetic defenses. While most solar wind particles bounce off the magnetic field and flow around Earth, some manage to penetrate the magnetosphere through a process called magnetic reconnection. Magnetic field lines from the Sun connecting and disconnecting with Earth's magnetic field lines, creating pathways for solar particles to enter. When the solar wind's magnetic field aligns in just the right way with Earth's magnetic field, the field lines can merge and break apart, allowing charged particles to slip through the cracks. Once inside the magnetosphere, these solar particles become trapped by Earth's magnetic field lines. Charged particles spiraling along Earth's magnetic field lines, following invisible highways that lead toward the polar regions. The particles follow the magnetic field lines like cars on a highway, spiraling around the lines as they move toward the poles. Streams of solar particles funneling down toward Earth's polar regions, guided by the planet's magnetic field toward the upper atmosphere. The magnetic field acts like a funnel, concentrating the particles and directing them toward the areas around the magnetic poles where the field lines dive back into the planet. This natural channeling system explains why auroras appear in oval-shaped regions around both magnetic poles. Glowing oval rings of aurora light encircling both of Earth's magnetic poles, marking where solar particles meet the upper atmosphere. The aurora oval expands and contracts depending on the strength of the solar wind, but it always remains centered on the magnetic poles rather than the geographic poles. The aurora oval shifting and pulsing with the rhythm of solar activity, sometimes expanding to cover vast areas of the polar sky. During quiet periods, the aurora appears as a narrow band close to the magnetic poles. During active periods, the oval grows larger and can extend to lower latitudes, bringing the northern lights to places that rarely see them. The entire system represents a delicate balance between the sun's energy and Earth's magnetic protection. protection. Earth's magnetic field standing guard against the solar wind. Its invisible shield allowing just enough particles through to paint the polar skies with light. Without the solar wind, there would be no particles to create the aurora. Without Earth's magnetic field, the solar wind would strip away our atmosphere entirely. The perfect harmony between solar wind and magnetosphere, creating the conditions for aurora light. A cosmic dance, billions of years in the making. The aurora exists because our planet found the perfect balance between protection and permeability, shielding us from the worst of the solar wind, while allowing just enough through to create one of nature's most spectacular light shows. The aurora begins its dance at the very edge of space, where our atmosphere grows thin and the boundary between Earth and the cosmos becomes blurred. The thin upper atmosphere glowing faintly blue against the black of space, wispy tendrils of gas extending into the void like ghostly fingers. This region, called the thermosphere, stretches from about 50 miles above the surface to over 400 miles high. Here, the air becomes so thin that a single breath at sea level contains more molecules than exist in a cubic mile of this rarefied oxygen atoms floating in the sparse upper atmosphere, each one glowing with a faint green light as solar radiation energizes them. The thermosphere holds mostly oxygen and nitrogen, the same gases we breathe at ground level, but spread so far apart that they barely interact with each other. Each molecule drifts alone through the near vacuum, sometimes traveling miles before encountering another particle. Individual nitrogen molecules tumbling slowly through the thermosphere, their electrons ready to capture energy from incoming solar particles. These simple atoms and molecules become the canvas upon which the aurora paints its masterpiece. The oxygen that creates the aurora's signature green glow was born in the nuclear furnaces of ancient stars, a massive red giant star in its final moments. Nuclear fusion creating oxygen atoms in its blazing core before exploding into space. Billions of years ago, when stars much larger than our sun reached the end of their lives, they forged oxygen in their cores through nuclear fusion, When these giants exploded as supernovas, they scattered this precious oxygen across the galaxy. Supernova shockwaves spreading through space, carrying clouds of newly formed oxygen atoms toward the young solar system. Some of that stellar oxygen eventually found its way into Earth's atmosphere, where it now waits in the thermosphere to be energized by particles from our own star. Nitrogen atoms glowing with deep red and purple light in the highest reaches of the atmosphere. Their electrons dancing with captured energy. The nitrogen that produces the aurora's red and purple hues followed a similar cosmic journey, created in the hearts of dying stars and distributed by stellar explosions. This nitrogen became part of the primordial cloud that collapsed to form our solar system. The early solar nebula swirling with dust and gas. Nitrogen atoms mixing with oxygen and hydrogen in the cosmic soup that would become Earth. Today, nitrogen makes up most of our atmosphere, but only the molecules floating in the thermosphere participate in the aurora's light show. The altitude where auroras appear depends entirely on the energy of the incoming solar particles. High-energy solar particles penetrating deep into the atmosphere, their paths glowing as they collide with oxygen molecules at different heights. The most energetic particles can drive down to 60 miles above Earth's surface, where they encounter denser concentrations of oxygen and nitrogen. Dense layers of atmospheric gases at 60 miles altitude, glowing bright green as energetic particles slam into oxygen atoms. These deep collisions create the aurora's lower border, a shimmering curtain that marks where space truly begins to give way to atmosphere. The thermosphere extending upward like a vast, invisible ocean, its upper reaches glowing faintly red, where the rarest particles dance with solar energy. Higher up, at altitudes of 200 miles or more, the atmosphere becomes so thin that only the most gentle solar particles can interact with the scattered atoms they find there. These high-altitude encounters produce the aurora's red glow, a subtle color that often crowns the green curtains below. Sparse oxygen atoms at extreme altitude glowing deep red against the star-filled void, their light marking the very edge of Earth's atmosphere. The red aurora appears less frequently because it requires specific conditions. But when it does manifest, it creates some of the most ethereal displays in the polar sky. Helium atoms drifting in the uppermost atmosphere, their electrons occasionally capturing energy to produce rare yellow auroral light. Even helium, that noble gas created in the first moments after the Big Bang, plays a small role in the aurora spectrum. Though helium makes up less than 1% of our atmosphere, it can produce faint yellow and orange hues during particularly intense auroral displays. The cosmic microwave background radiation filling space, a faint echo of the Big Bang that created the first helium atoms, now glowing in Earth's aurora. This helium connects our planet's light show to the very birth of the universe, when the first atomic nuclei formed in the cooling aftermath of creation. Hydrogen atoms scattered through the thermosphere, their simple structure allowing them to glow with pure white light when energized by solar particles. Hydrogen, the most abundant element in the universe, also contributes to the aurora's palette. Though rare in Earth's upper atmosphere, hydrogen atoms can produce white and pale blue auroral light. Vast clouds of hydrogen gas floating between the stars, the raw material from which all other elements were eventually forged in stellar cores. The hydrogen in our atmosphere represents the universe's most basic building block, the simple proton-electron pairs that emerged from the cosmic dark ages and eventually gathered into the first stars. The temperature in the thermosphere can reach over 3,000 degrees Fahrenheit, hot enough to melt copper. The thermosphere glowing with intense heat, its sparse molecules moving at incredible speeds despite the near vacuum conditions. Yet, an astronaut floating in this region would freeze to death because the air is so thin that these fast-moving molecules rarely collide with anything to transfer their heat. Individual atmospheric molecules racing through the thermosphere at thousands of miles per hour. Their kinetic energy creating the extreme temperatures where auroras form. This paradox of hot but non-warming air creates the perfect conditions for auroral displays, where energetic particles can excite atoms without the interference of dense atmospheric collisions. The boundary between Earth's atmosphere and space, shimmering with aurora light, marking where our planet's protective envelope meets the cosmic void. The aurora exists in this liminal space because it requires both the presence of atmospheric particles and the near vacuum conditions that allow those particles to glow freely. Earth's thin atmospheric shell glowing like a soap bubble around the planet, its upper reaches painted with the colors of aurora light. This delicate balance creates one of the most beautiful examples of how cosmic forces shape the matter forged in ancient stars, turning simple atoms into a celestial light show that connects our world to the greater universe. The colors that dance across the polar sky tell the story of invisible forces at work in the darkness above. Brilliant green curtains of aurora, light rippling across the night sky, their luminous waves flowing like silk in a cosmic breeze. Each hue reveals which atoms the solar wind has awakened from their quiet slumber. Oxygen atoms, when struck by energetic particles at altitudes around 60 miles above Earth, emit that familiar green glow that dominates most auroral displays. Emerald green aurora ribbons stretching across the horizon, their ethereal light reflecting off snow-covered mountains and frozen lakes below. This green light comes from oxygen atoms that have been excited by colliding particles, then release their extra energy as photons of a very specific wavelength. Higher in the atmosphere, around 150 miles up, oxygen atoms create an entirely different color. Deep red aurora bands glowing softly at the edge of space, their crimson light mixing with the star-filled void above. These red auroras appear less frequently because the air is so thin at these heights that oxygen atoms have more time between collisions, allowing them to emit red light instead of green. The process takes longer, requiring the atoms to hold their energy for nearly 2 minutes before releasing it as that distinctive scarlet glow. Rare red aurora streamers dancing at the very edge of Earth's atmosphere, their burgundy light bleeding into the cosmic darkness. This timing difference explains why red auroras appear only at the highest altitudes, where the air is sparse enough to give oxygen atoms the patience they need. Nitrogen molecules add their own signature to this celestial palette. Deep blue aurora fingers reaching upward through the green curtains, their sapphire light creating layers of color in the polar sky. When solar particles strike nitrogen at lower altitudes, they produce blue and purple hues that often appear at the bottom edges of aurora displays. These colors require more energy to create, which is why they show up less frequently than the dominant green. Purple aurora edges glowing along the bottom of green curtains, their violet light marking where the atmosphere grows denser. Nitrogen can also produce pink and magenta colors when conditions are just right, creating some of the most spectacular and rare auroral displays. The intensity of these colors depends entirely on how many particles the sun sends our way. Intense golden green aurora sheets blazing across the entire sky, their brilliant light illuminating the landscape like a supernatural dawn. During powerful solar storms, when the solar wind carries billions of extra particles toward Earth, the aurora becomes bright enough to read by. The magnetic field lines that guide these particles act like invisible highways in the sky, channeling the solar wind toward the polar regions where the field lines dive back into the planet. Invisible magnetic field lines curving through space around Earth, their paths traced by streams of glowing particles creating aurora light. These field lines compress and stretch like rubber bands as the solar wind pushes against them, storing energy that eventually releases in brilliant bursts of light. The altitude where particles strike the atmosphere determines not just color, but also the shape of the display. Towering aurora columns rising like luminous pillars from the horizon, their green and red light reaching toward the stars. Lower altitude collisions create the familiar curtain-like structures that seem to hang from the sky, while higher altitude interactions produce more diffuse glows that spread across vast areas. The Earth's magnetic field acts like a lens, focusing the incoming particles into narrow beams that create those dramatic vertical rays. Narrow beams of aurora, light shooting upward like searchlights, their focused rays piercing through layers of atmospheric glow. These rays can extend for hundreds of miles, creating the illusion that the aurora reaches much higher than it actually does. temperature plays a role in this cosmic light show, though not in the way you might expect. The thermosphere glowing with aurora light, its sparse molecules heated to thousands of degrees, yet unable to warm anything they touch. The atoms and molecules that create aurora light are moving at incredible speeds due to the extreme temperatures in the upper atmosphere. But the air is so thin that this heat cannot transfer to anything else. This creates the perfect conditions for the aurora, where particles can collide and emit light without the interference of dense air that would quickly absorb and scatter the photons. Individual oxygen and nitrogen atoms floating in the near vacuum of space, their electrons jumping between energy levels to create flashes of colored light. The aurora exists in this strange, where matter behaves more like individual particles than the continuous fluid we experience at sea level. Pressure differences between the upper and lower atmosphere help shape the aurora's movement and flow. Aurora curtains billowing and folding like luminous fabric in an invisible wind. Their graceful movements following the contours of Earth's magnetic field. The near vacuum conditions at auroral altitudes allow the displays to move and dance with a fluid grace that would be impossible in denser air. Solar wind pressure pushes against Earth's magnetic field, creating waves and disturbances that ripple through the aurora like wind through wheat. Waves of aurora light rolling across the sky like luminous ocean swells, their crests and troughs following the rhythm of solar wind gusts. These pressure variations can cause the aurora to suddenly brighten, fade, or change direction, creating the dynamic displays that have captivated observers for thousands of years. The magnetic field strength varies across the planet, creating different intensities of auroral activity at different locations. Earth's magnetic field lines converging at the polar regions, their invisible pathways glowing with streams of aurora light. Near the magnetic poles, where the field lines are nearly vertical, particles can penetrate deeper into the atmosphere, creating more intense displays. Further from the poles, the magnetic field acts as a stronger shield, allowing fewer particles through and creating weaker auroras. The oval ring of aurora light encircling Earth's magnetic pole, its luminous boundary marking where solar particles can penetrate the planet's protective field. This creates the auroral oval, a ring-shaped zone around each magnetic pole where aurora activity is most common and intense. A glowing crown that marks where our planet's magnetic armor meets the endless stream of particles flowing from our star. The auroral oval stretches across a zone roughly 1,500 miles wide, a glowing belt that could span from New York to Denver. A luminous green belt of aurora light stretching across the curved horizon of Earth, its glow extending over vast mountain ranges and frozen tundra below. If you could see this ring from space, it would look like a crown of light circling each pole, pulsing and shifting as our planet turns beneath it. The oval moves with the solar wind, expanding toward the equator when solar storms intensify, and shrinking back toward the poles during quiet periods. Within this zone, individual aurora displays can tower to incredible heights above the ground, towering curtains of green and purple light reaching from the dark horizon up into the star-filled sky, their vertical columns stretching impossibly high. The lowest auroras begin about 60 miles above your head, higher than where jets fly, but lower than where satellites orbit. The tallest displays can reach 600 miles into space, extending beyond the International Space Station. Ethereal ribbons of light cascading down from the edge of space, their luminous threads connecting the darkness above to the snowy landscape far below. If you stood at the base of the Empire State Building and looked up, the aurora would be like a glowing curtain that starts 400 Empire State Buildings above you and extends upward for another 4,000. The scale of energy involved in creating these displays staggers the mind. Brilliant waves of aurora light rippling across the polar sky like luminous ocean waves, each crest glowing brighter than the last. A single large aurora releases as much energy as a magnitude 7 earthquake. But instead of shaking the ground, this energy paints the sky with light. The particles creating this display travel at speeds of up to 4 million miles per hour as they spiral down magnetic field lines. Streams of invisible particles flowing along curved magnetic field lines, their pathways outlined by glowing aurora light against the deep black of space. That speed means a particle from the sun could travel from Los Angeles to New York in less than 2 seconds. The aurora oval itself rotates around each magnetic pole once every 24 hours as Earth spins. The curved edge of Earth showing the glowing auroral oval slowly rotating around the magnetic pole, its luminous ring shifting across continents and oceans. This means that locations within the oval experience peak aurora activity at different times throughout the night, shimmering curtains of light dancing above a frozen lake, their reflection creating perfect mirror images in the still dark water. Fairbanks, Alaska sits directly under the northern auroral oval, which explains why it sees auroras on more than 200 nights each year. The magnetic field lines that guide these particles stretch far into space, some extending more than 40,000 miles from Earth. Invisible magnetic field lines stretching from Earth's poles deep into space, their curved pathways glowing faintly where solar particles follow them earthward. If Earth were the size of a marble, these field lines would reach out like invisible threads, extending 20 feet in all directions. Earth's magnetic field creating a vast protective bubble around the planet, its boundaries glowing where they meet the stream of solar wind. The solar wind compresses this magnetic bubble on the side facing the sun and stretches it into a long tail on the night side, creating a teardrop shape that extends beyond the moon's orbit. Ancient observers had no way to measure these vast scales, but they recognized the aurora's power. Brilliant green and purple, aurora light illuminating snow-covered mountains and valleys. The entire landscape glowing under the celestial display. Norse mythology described the aurora as light reflecting off the armor of warrior maidens riding across the sky. Undulating waves of multicolored light flowing across the star-filled sky like luminous silk banners waving in a cosmic breeze. The Inuit peoples of the Arctic saw the lights as spirits playing football with a walrus skull, their game creating the dancing patterns overhead. Pillars of bright aurora light standing like luminous columns against the dark sky, their bases touching the horizon and their tops reaching toward the stars. Finnish folklore called the phenomenon revanchelit, meaning fox fires, imagining a magical fox running so fast across the snow that its tail swept up snowflakes that sparkled in the moonlight. These stories capture something true about the aurora's scale and power. Serpentine ribbons of green light weaving through the darkness above a vast forest of snow-laden evergreen trees, their glow casting ethereal shadows on the white ground. The displays can be so bright they cast shadows on the ground, turning night into an eerie twilight. The entire northern horizon glowing with soft aurora light, its luminous arc stretching from east to west like a celestial rainbow. They can span the entire visible sky, creating a dome of shifting light that makes observers feel small beneath the vast cosmic forces at work above their heads. The science behind this celestial light show begins with a simple collision between invisible particles and the thin air at the edge of space. Streams of glowing particles cascading down through the upper atmosphere like luminous rain, their paths creating brilliant streaks against the star-filled darkness. Solar wind particles carry tremendous energy as they race toward Earth at speeds reaching 4 million miles per hour. When these charged particles slam into oxygen and nitrogen atoms in our atmosphere, they transfer their energy in a burst of visible light. Curtains of green aurora light rippling like silk fabric in a gentle breeze, their translucent glow revealing layers upon layers of luminous sheets. The collision happens roughly 60 to 400 miles above Earth's surface, in a region so thin that a single breath of air at sea level contains more molecules than exist in a cubic mile of space at aurora altitude. Each particle collision lasts only a fraction of a second, but billions of these tiny light bursts create the flowing displays we see from below. Pillars of red aurora light stretching vertically through the night sky like glowing columns in a cosmic cathedral, their bases fading into darkness. The color depends entirely on which type of atom gets hit and at what altitude the collision occurs. Oxygen atoms struck at lower altitudes glow green, the most common aurora color. Waves of bright green light flowing across the sky like luminous ocean swells, their crests and valleys creating a rhythm of moving illumination. The same oxygen atoms, when hit at higher altitudes where the air is even thinner, produce red light instead. Delicate pink aurora ribbons threading through the darkness above snow-covered mountains, their soft glow reflecting off the pristine white peaks below. Nitrogen atoms create blue and purple hues when energized by the solar particles. The rarest aurora colors appear when particles penetrate to unusual altitudes, or when solar storms deliver particles with different energy levels, spiraling bands of purple light twisting through the upper atmosphere like cosmic tornadoes, their rotation creating mesmerizing patterns against the void. Sometimes the collisions happen so high up that they produce colors the human eye can barely detect. A vast dome of shimmering aurora light covering the entire sky, its surface rippling with waves of green and blue like the ceiling of an enormous luminous cave. The intensity of the glow depends on how many particles arrive from the sun and how much energy they carry. During quiet solar periods, the aurora appears as a faint green arc near the horizon, gentle arcs of soft green light stretching across the northern horizon like luminous bridges connecting distant mountain ranges. But when solar storms send massive waves of particles toward Earth, the aurora blazes bright enough to read by. Rapid pulses of aurora light flickering like cosmic lightning, each flash illuminating different sections of the night sky in brilliant green and red. The particles don't arrive in a steady stream, but in waves and bursts that create the aurora's characteristic movement. Some displays pulse rhythmically, flashing on and off every few seconds, shimmering veils of light dancing vertically through the atmosphere, their movements creating the illusion of cosmic curtains swaying in an invisible wind. Others flow smoothly across the sky like slow rivers of light, brilliant coronas of aurora, light radiating outward from a central point directly overhead, their rays extending in all directions like the spokes of a luminous wheel. The most dramatic displays create coronas, where the aurora appears to radiate from a point directly overhead, This happens when the observer stands directly beneath the point where Earth's magnetic field lines converge. Serpentine bands of yellow-green light weaving through the darkness like glowing serpents. Their sinuous paths creating intricate patterns across the star-filled sky. From this position, the normally horizontal curtains of light appear to stretch vertically in all directions, creating a dome of radiance that surrounds the observer completely. Multiple layers of aurora light stacked at different altitudes, each glowing with its own distinct color, creating a cosmic layer cake of green, red, and purple illumination. Scientists can measure the exact altitude of aurora displays by observing them from 2 different locations and calculating the triangulation. Most green aurora occurs between 60 and 150 miles up, towering walls of aurora light rising from the horizon like luminous cliffs, their vertical faces glowing with intense green fire against the cosmic darkness. The red aurora typically appears much higher, sometimes reaching altitudes of over 600 miles above the surface. The collision between solar particles and atmospheric gases creates one of nature's most precise chemical reactions. Brilliant streams of charged particles racing through the upper atmosphere, each one glowing like a tiny meteor as it strikes invisible gas molecules in the darkness. When a high-energy electron from the solar wind crashes into an oxygen atom, it transfers its energy to that atom's electrons. The oxygen electron jumps to a higher energy level, but it cannot stay there long. Cascading waves of green light rippling through thin atmospheric layers, each wave triggered by countless invisible particle collisions occurring simultaneously. Within a fraction of a second, the excited electron falls back to its normal state, releasing that extra energy as a photon of light. The color of that photon depends entirely on which type of gas the solar particle strikes. Towering columns of emerald fire stretching upward through the atmosphere, their intense glow revealing the exact altitude where oxygen atoms dominate the thin air. Oxygen atoms create the familiar green glow that dominates most aurora displays. This green light has a very specific wavelength of 557.7 nanometers. Delicate curtains of red light dancing high above the green aurora, their crimson glow marking where the atmosphere becomes incredibly thin and sparse. The same oxygen atoms can also produce red light at 630 nanometers. But this only happens at much higher altitudes where the air is extremely thin. Nitrogen molecules contribute their own signature colors to the aurora palette. Deep purple bands weaving between sheets of green light. Their rich color, created by nitrogen molecules, vibrating with absorbed solar energy. When solar particles strike nitrogen, they can produce deep red light at the lower edges of aurora displays. At higher altitudes, nitrogen creates brilliant blue and purple hues. Electric blue streamers flickering rapidly through the aurora curtains. Their intense color revealing nitrogen molecules being energized by the solar wind. The nitrogen molecules actually vibrate rather than just releasing single photons, creating a different type of light emission than oxygen atoms produce. The intensity of the aurora depends on how many particles arrive from the sun. Massive walls of light stretching across the horizon, their brightness fluctuating as waves of solar particles wash over the upper atmosphere in rhythmic pulses. During quiet solar periods, only a few thousand particles per square centimeter strike the atmosphere each second. During solar storms, this number can increase to millions of particles per square centimeter, shimmering veils of light undulating like silk in a gentle breeze. Their soft glow indicating a peaceful interaction between Earth and the solar wind. Each individual collision lasts only nanoseconds, but billions of collisions happening simultaneously create the sustained glow we observe from the ground. The altitude where collisions occur determines which gases participate in the light show. Layered bands of different colored light stacked vertically through the atmosphere, each layer glowing with its own distinct hue based on the gas molecules present at that height. Below 60 miles altitude, the atmosphere becomes too dense for aurora to form. The incoming particles lose their energy through too many collisions before they can create visible light. Ghostly fingers of light reaching downward from the aurora curtains, their tips fading as they encounter the denser layers of atmosphere below. Above 400 miles, the atmosphere becomes so thin that very few collisions occur, making aurora rare at these extreme heights. The magnetic field guides particles toward specific collision zones. Spiraling streams of light following invisible magnetic pathways through the sky. Their curved trajectories revealing the hidden structure of Earth's magnetic field. Particles follow the magnetic field lines like cars following a highway, concentrating their impacts in narrow bands around the magnetic poles. Concentrated beams of aurora light converging toward the magnetic north. Their focused intensity creating brilliant hotspots of activity in the polar sky. This focusing effect explains why aurora appears in oval-shaped zones around the magnetic poles, rather than spreading randomly across the entire planet. The collision process releases more than just visible light. Invisible waves of energy radiating outward from aurora collisions. Their electromagnetic pulses creating disturbances that ripple through the upper atmosphere. Each particle collision also produces radio waves, X-rays, and heat. Scientists can detect these invisible emissions using special instruments, revealing aurora activity even during daylight hours. Thermal currents rising from aurora-heated atmospheric layers. Their invisible warmth creating subtle changes in air density and atmospheric circulation patterns. The aurora actually heats the upper atmosphere by several hundred degrees during intense displays, expanding rings of atmospheric disturbance spreading outward from intense aurora activity. Their effects measurable hundreds of miles away from the visible light display. This heating can cause the atmosphere to expand, affecting satellite orbits and radio communications across vast distances. The aurora's dance follows a perfect mirror across our planet. Twin oval rings of shimmering green light encircling both polar regions simultaneously. Their synchronized glow creating perfect symmetry across Earth's magnetic field. While the northern lights captivate observers in Alaska and Scandinavia, an identical display unfolds in the southern hemisphere. The Aurora Australis or southern lights, appears over Antarctica with the same ethereal beauty. Brilliant curtains of aurora light cascading over the pristine Antarctic ice sheet, their emerald glow reflecting off endless expanses of white snow and glacial formations. These southern displays mirror their northern cousins with remarkable precision, following the same magnetic field lines that guide particles toward both poles. The timing of aurora activity pulses with Earth's rotation. A slow wave of aurora intensity rolling around the polar regions as Earth turns, the light brightening and dimming in a 24-hour rhythm. As our planet spins, different longitudes face the incoming solar wind at varying angles. This creates a daily cycle where aurora activity peaks around midnight local time. The aurora oval slowly shifting position as Earth rotates, its bright arc moving across the polar landscape like a celestial spotlight following the planet's spin. Scientists track this rotation effect using networks of ground-based cameras and satellites. The aurora appears strongest when observers stand on the night side of Earth, facing away from the sun. Seasonal changes dramatically alter aurora visibility and intensity. The aurora oval expanding toward lower latitudes during the dark polar winter, its green glow stretching further south across snow-covered forests and frozen lakes. During winter months, in each hemisphere, longer nights provide more viewing opportunities. The aurora oval also shifts position with the seasons, following changes in Earth's magnetic field orientation relative to the solar wind. Earth's tilted magnetic field creating asymmetrical aurora patterns between the northern and southern hemispheres, their ovals slightly offset and varying in size throughout the year. Spring and autumn bring the most intense displays because Earth's magnetic field aligns optimally with the solar wind during these equinox periods. The aurora follows longer cycles tied to solar activity, waves of charged particles streaming from the sun in 11-year cycles, their intensity varying from calm periods to explosive solar maximum events. Every 11 years, the sun's magnetic field completely reverses, creating periods of intense solar storms followed by quieter phases. During solar maximum, aurora displays become more frequent and vivid. Massive solar flares erupting from the sun's surface, their brilliant plasma clouds racing toward Earth at millions of miles per hour. These solar storms can push the aurora oval hundreds of miles closer to the equator, allowing observers in normally aurora-free regions to witness the spectacle. The magnetic connection between Earth and Sun creates predictable patterns in aurora timing. Invisible magnetic field lines stretching between Earth and the Sun, their twisted geometry channeling solar particles toward our planet's polar regions. When the solar wind's magnetic field aligns with Earth's field, particles flow more easily into our atmosphere. Streams of solar particles following curved magnetic pathways through space, their glowing trails converging on Earth's magnetic poles like luminous rivers in the void. Scientists can forecast aurora activity days in advance by monitoring solar wind conditions and magnetic field orientations. The aurora's intensity varies with a 27-day cycle matching the sun's rotation. The sun slowly rotating on its axis, its magnetic field and particle streams sweeping past Earth in regular 27-day intervals. Active regions on the sun's surface face Earth repeatedly as our star spins, creating recurring periods of enhanced aurora activity. Coronal holes in the sun's atmosphere streaming high-speed solar wind toward Earth, their dark regions visible as gaps in the sun's glowing corona. These high-speed streams arrive at Earth in predictable waves, triggering aurora displays that follow the sun's rotation period. The southern lights remain largely hidden from human observation due to Antarctica's remote location. Vast aurora displays illuminating the empty Antarctic continent. Their spectacular light shows witnessed only by research stations scattered across the ice. While millions observe the northern lights from populated regions, the southern aurora dances over one of Earth's most isolated landscapes. Ethereal green curtains of light rippling across the Antarctic plateau, their reflection shimmering on the surface of frozen seas beneath star-filled skies. Satellite images reveal that southern aurora displays match their northern counterparts beauty and intensity. The Aurora Australis creating perfect mirror symmetry with the northern lights, their twin displays connected by Earth's magnetic field lines threading through the planet's core. This hidden southern spectacle reminds us that nature's most beautiful performances often unfold far from human eyes, following ancient rhythms that connect our planet to the cosmos. The aurora follows Earth's seasonal dance around the sun, creating patterns of light that shift with our planet's tilted journey through space. Earth tilted on its axis as it orbits the sun, one hemisphere bathed in golden sunlight, while the other remains shrouded in winter darkness. During the equinoxes in March and September, when day and night balance equally across our world, aurora activity reaches its peak intensity, the northern hemisphere transitioning from winter to spring. Vast landscapes emerging from snow cover as the aurora dances overhead in brilliant green waves. These seasonal peaks occur because Earth's magnetic field aligns most favorably with the solar wind during these transitional periods. The tilt of our planet creates a rhythm that governs when and where the lights appear most frequently. The Arctic Circle during the long polar night, endless darkness broken only by the ethereal glow of aurora curtains rippling across star-filled skies. Winter months offer the longest viewing windows in the north, with darkness stretching for up to 20 hours in regions like northern Alaska and northern Scandinavia. Snow-covered forests beneath towering aurora displays. The green and purple lights reflecting off pristine white landscapes that stretch to the horizon. Summer brings continuous daylight to these same regions, making aurora observation impossible despite the lights continuing to dance invisibly overhead. The southern hemisphere experiences its aurora season during our northern winter, when Antarctica enjoys its brief summer months. The Antarctic continent during its summer season. Research stations scattered across the ice beneath spectacular aurora displays painting the twilight sky. This timing creates a global rhythm where aurora watchers in opposite hemispheres take turns witnessing nature's light show. Massive icebergs floating in Antarctic waters, their surfaces glowing with reflected aurora light as green curtains dance across the polar sky. The seasonal shift means that while northern observers bundle against winter cold to see the lights, southern researchers enjoy relatively mild Antarctic summer conditions. Solar activity follows its own seasonal patterns that interact with Earth's orbital rhythm. The sun's surface during periods of high activity, brilliant solar flares erupting from active regions, while coronal mass ejections stream into space. Coronal holes, those dark regions in the sun's atmosphere that stream high-speed solar wind toward Earth, rotate with our star's 27-day period. High-speed solar wind particles streaming from the sun toward Earth, their invisible flow creating disturbances in the planet's magnetic field. When these fast-moving streams align with Earth's favorable magnetic orientation during equinox periods, the result creates some of the year's most spectacular aurora displays. The interaction between Earth's seasons and solar patterns creates predictable windows of enhanced activity. Earth's magnetosphere during a geomagnetic storm, invisible field lines compressed and twisted by incoming solar wind, creating pathways for aurora particles. Spring and autumn equinoxes consistently produce the most intense geomagnetic storms. When solar particles find easier access to our planet's polar regions, the northern lights cascading down from high altitude, their curtains of light beginning as faint glows and intensifying into brilliant dancing displays. These seasonal peaks occur regardless of the solar cycle's 11-year rhythm, creating reliable periods when aurora photographers and enthusiasts plan their expeditions. Weather patterns also follow seasonal rhythms that affect aurora visibility. Clear winter skies above the Arctic tundra, stars shining brilliantly through the thin atmosphere as aurora curtains prepare to unfold across the darkness. Winter's clear, cold air provides the best atmospheric conditions for viewing, with less moisture and fewer clouds to obscure the display. Frozen lakes reflecting aurora light, their mirror-smooth surfaces doubling the visual impact of green and purple curtains dancing overhead. The dry air of winter nights allows aurora colors to appear more vivid and defined, while summer's humid conditions can soften and blur the lights. Mountain ranges and geographical features create their own seasonal viewing patterns. Snow-capped mountain peaks silhouetted against brilliant aurora displays, their jagged profiles creating dramatic foregrounds for the dancing lights above. Northern mountain regions like those in Alaska, northern Canada, and Scandinavia offer elevated viewing platforms that extend the aurora viewing season. Alpine valleys filled with aurora light, the ethereal glow illuminating snow-covered slopes and creating an otherworldly landscape of green and blue. Higher altitudes provide clearer air and darker skies, while the surrounding peaks block light pollution from distant cities. The seasonal migration of animals in polar regions coincides with peak aurora activity. Vast herds of caribou moving across the Arctic tundra beneath spectacular aurora displays, their migration paths illuminated by the dancing northern lights. Arctic wildlife has adapted to the rhythm of long winter nights when aurora activity peaks. Though scientists continue studying whether animals respond to the electromagnetic changes that accompany geomagnetic storms, the Aurora Borealis, reflecting off the surface of Arctic sea ice, creating a mirror effect that doubles the visual impact of the dancing lights. Indigenous peoples of the Arctic have long observed connections between aurora activity and animal behavior. Knowledge passed down through generations of careful observation. Ocean currents and sea ice patterns also follow seasonal cycles that interact with aurora viewing conditions. The Arctic Ocean during winter, its surface frozen into vast sheets of sea ice that reflect and amplify the glow of aurora displays overhead. Sea ice provides stable viewing platforms and reduces atmospheric moisture, creating ideal conditions for aurora photography and observation. Polynyas, areas of open water surrounded by sea ice, steaming in the frigid Arctic air as aurora curtains dance in the sky above. These seasonal ice patterns affect local weather and atmospheric conditions, influencing how clearly the aurora appears and how long displays remain visible. The rhythm of seasons creates a beautiful partnership between Earth's orbital dance and the solar wind's eternal flow, ensuring that somewhere on our planet, the aurora always finds a stage for its cosmic performance. The cosmic performance reaches its most spectacular heights during the Sun's 11-year cycle of magnetic fury. The Sun's surface erupting with massive solar flares, brilliant white and orange plasma arcing thousands of miles into space against the black void. Our star breathes in a rhythm that spans more than a decade, building from quiet whispers to thunderous roars that shake the entire solar system. During solar maximum, the sun unleashes its most powerful storms, sending waves of charged particles racing toward Earth at speeds that dwarf our fastest rockets. Coronal mass ejections blasting from the sun's corona. Massive bubbles of magnetized plasma expanding outward like luminous jellyfish in the darkness of space. These solar storms can carry the energy of billions of nuclear bombs, though they spread this power across millions of miles of empty space. When these cosmic hurricanes reach our planet, they compress Earth's magnetic field like a spring, storing energy that eventually explodes into the most brilliant aurora displays ever witnessed. Earth's magnetosphere glowing bright blue and green as it deflects a massive solar wind. Streamers of charged particles flowing around our planet's magnetic bubble. The strongest geomagnetic storms can push aurora displays as far south as Florida and Mexico, regions that might see the northern lights only once in a human lifetime. Aurora Borealis cascading down from the polar regions toward the equator. Sheets of green and red light stretching across entire continents during a massive geomagnetic storm. During the most extreme events, the aurora becomes visible from places where palm trees grow and desert sands stretch to the horizon. The Great Geomagnetic Storm of 1859, known as the Carrington Event, created aurora so bright that people could read newspapers by their light. Telegraph lines sparking and glowing with induced electrical current during a massive geomagnetic storm. The aurora overhead painting the sky in brilliant sheets of light. telegraph operators received electric shocks from their equipment, and some telegraph lines continued working even after their power sources were disconnected, drawing energy directly from the electromagnetic chaos above. The Aurora Australis mirroring its northern twin, creating a perfect ring of light around Antarctica as viewed from space, both poles glowing simultaneously. The southern lights dance with equal intensity during these solar maximum years, though fewer people witness their beauty in the remote Antarctic wilderness. Satellites orbiting high above Earth sometimes capture both aurora at once, revealing the perfect symmetry of our planet's magnetic response to solar storms. Satellite solar panels glowing with St. Elmo's fire as they pass through the charged particles of an intense aurora display. The spacecraft tumbling slowly against star-filled space. These extreme events can damage satellites, disrupt radio communications, and even cause power grids to fail when the electromagnetic pulse overwhelms electrical systems. The sun's magnetic field lines twisting and reconnecting in complex patterns, creating bright loops of plasma that arch high above the solar surface. Scientists measure the sun's magnetic activity using sunspot counts, dark patches that reveal where powerful magnetic fields pierce the solar surface. During solar minimum, the sun might go weeks without a single visible sunspot, creating a deceptively calm appearance. The sun's surface appearing smooth and featureless during solar minimum, its golden glow steady and peaceful, with no visible sunspots or solar flares. But even during these quiet years, the solar wind continues its eternal journey, ensuring that aurora never completely disappear from polar skies. Massive sunspot groups covering areas larger than Jupiter, dark magnetic storms brewing on the sun's surface like cosmic hurricanes. The largest sunspot groups can be seen with the naked eye through proper solar filters, appearing as dark freckles on our star's brilliant face. These magnetic storms on the sun create the conditions for the most spectacular aurora displays. When Earth becomes wrapped in curtains of light that stretch from horizon to horizon, the entire Arctic Circle glowing with aurora light during a solar maximum event. The curved horizon of Earth showing sheets of green and red dancing across multiple time zones. During peak solar activity, aurora photographers travel to the darkest corners of Alaska, northern Canada, and Scandinavia, knowing that the sun's 11-year heartbeat has reached its most powerful rhythm. Solar wind particles streaming past Earth at over 1 million miles per hour, creating bow shock waves in the magnetosphere like a cosmic speedboat cutting through invisible water. The fastest solar wind can cross the 93 million miles between Sun and Earth in just over 2 days. Though typical solar wind takes 3 to 4 days to complete this cosmic journey, aurora curtains rippling and undulating like silk scarves in a gentle breeze, their movement following the invisible dance of magnetic field lines high above the Arctic landscape. These extreme solar events remind us that our peaceful planet orbits within the atmosphere of a star, forever bathed in the breath of the sun's magnetic storms. The northern lights reflecting in the still waters of an Arctic lake, doubling the display as perfect mirror images dance both above and below the horizon. The sun's 11-year cycle ensures that each generation witnesses at least several periods of maximum aurora activity. When the cosmic light show reaches its most breathtaking intensity. The magnetic field lines that guide aurora particles follow paths invisible to our eyes. Yet they create the most intricate patterns in the night sky. Delicate aurora, curtains hanging like luminous silk veils against the star-filled Arctic sky. Their vertical columns stretching from horizon to zenith in perfect parallel lines. These field lines emerge from Earth's magnetic North Pole and curve gracefully through space before diving back into the magnetic South Pole. Glowing green aurora bands rippling in slow motion across the darkness, their edges sharp as knife cuts against the deep indigo of the polar night. When charged particles follow these invisible highways, they create curtains of light that can stretch for hundreds of miles, while remaining only a few miles thick. The aurora's curtain-like appearance comes from particles spiraling down these magnetic field lines like beads sliding down invisible strings. Brilliant aurora rays shooting straight up from the horizon like searchlights. each beam following a different magnetic field line toward the stars above. Scientists call this phenomenon field-aligned precipitation, where particles rain down along the exact paths that Earth's magnetism provides. Soft pink aurora glow mixing with green light at the edges of a dancing curtain, creating pastel gradients that shift and blend like watercolor paint. The most active aurora displays show these curtains moving and folding like fabric in a cosmic breeze, responding to changes in the solar wind's pressure and direction. Individual aurora rays within these curtains can be remarkably narrow, sometimes measuring less than 100 meters across. Multiple aurora curtains layered at different altitudes, creating depth and dimension as some glow brighter in the foreground, while others fade into the atmospheric distance. These thin columns of light mark spots where magnetic field lines converge, concentrating particles into focused beams. Aurora light reflecting off fresh snow across an endless Arctic tundra. The white landscape glowing green beneath the dancing sky display. The spacing between these rays often follows mathematical patterns, with distances that relate to the strength and structure of Earth's magnetic field at different altitudes. During quiet magnetic conditions, aurora curtains hang motionless for minutes at a time, creating what scientists call stable auroral arcs. A perfectly still aurora arc stretching across the entire northern horizon like a glowing bridge connecting distant mountain peaks. These stable arcs mark the boundary where Earth's magnetic field meets the solar wind, a cosmic shoreline that shifts with space, weather conditions. Faint aurora glow illuminating low-hanging clouds from above, the light filtering through the mist to create an ethereal, diffused radiance. The most sensitive cameras can detect these quiet arcs, even when they appear too faint for human eyes to see clearly. The texture of aurora light changes with altitude, creating layers of different brightness and color intensity. Aurora curtains with intricate folds and pleats, their surfaces textured like cosmic drapery, hanging in the thin atmosphere above the polar regions. At the lowest altitudes where aurora occurs, around 60 miles above Earth's surface, the light appears most concentrated and vivid. Brilliant aurora corona formation directly overhead, with rays converging toward a central point like the spokes of a luminous wheel against the star field. Higher up, near 200 miles altitude, the aurora spreads into broader, more diffuse glows that blend the sharp edges into softer transitions. The magnetic field lines themselves follow complex three-dimensional curves that scientists map using mathematical models and satellite measurements. Aurora light forming perfect spirals and loops as charged particles follow the twisted magnetic field lines through Earth's upper atmosphere. These field lines can become twisted and tangled during magnetic storms, creating unusual aurora shapes that defy the typical curtain pattern. Rare red aurora glow appearing high above the green curtains, marking where oxygen atoms emit light at extreme altitudes in the thin atmosphere. When field lines reconnect and snap back into new configurations, they can trigger sudden brightening events called auroral substorms. The most detailed aurora observations reveal that individual curtains contain hundreds of thin rays, each following its own magnetic pathway. Close view of aurora, rays showing their internal structure, with brighter cores surrounded by fainter glowing sheaths like luminous fiber optic cables. These rays can pulse and flicker on timescales of seconds, responding to rapid changes in the particle flow from space. Aurora curtains developing wave-like undulations along their length, creating sinuous patterns that ripple from east to west across the polar sky. The fastest aurora motions occur when magnetic field lines suddenly release stored energy, causing curtains to explode into brilliant displays that can brighten by a factor of 1,000 in just seconds. Multiple aurora curtains at different distances, creating a sense of vast depth, with some appearing close enough to touch, while others fade into the atmospheric haze. Ground-based cameras can capture the three-dimensional structure of these displays, revealing how curtains at different altitudes move independently of each other. Aurora light casting subtle shadows on the snow-covered landscape below. The glow bright enough to read by in the Arctic darkness. The most intense aurora events create enough light to cast distinct shadows from trees and buildings, transforming the polar night into an otherworldly twilight. Delicate aurora wisps and tendrils extending from the main curtains like cosmic smoke trails, dissolving into the star-filled darkness above. The mystery of aurora colors puzzled scientists for centuries before they understood the simple truth hiding in plain sight. Brilliant green aurora curtains dominating the polar sky, their emerald glow casting ethereal light across snow-covered mountains and frozen lakes below. Green appears most often because it comes from oxygen atoms floating about 60 miles above Earth's surface, right in the sweet spot where solar particles hit with perfect energy. Oxygen atoms glowing bright green as invisible solar particles strike them in the thin upper atmosphere, creating cascades of luminous emerald light. When a solar particle smashes into an oxygen atom at this altitude, it knocks an electron into a higher energy state. And when that electron falls back down, it releases a photon of green light. Early aurora researchers in the 1800s had no idea what caused the colors they saw dancing overhead. Victorian-era scientists, standing beneath towering aurora displays, their primitive instruments silhouetted against curtains of shifting green and red light. They knew the lights appeared during magnetic storms, but the connection between Earth's magnetic field and atmospheric gases remained hidden. Magnetic field lines invisible to the eye, stretching from Earth's poles into space like cosmic highways guiding charged particles toward the atmosphere. Swedish physicist Anders Ångström made the first breakthrough in 1867 when he used a spectroscope to split aurora light into its component colors, revealing distinct bright lines that matched no known element on Earth. The green line at 557.7 nanometers became aurora science's greatest puzzle. A spectroscope revealing the hidden rainbow within aurora light, showing distinct bright lines of green, red, and blue separated like cosmic fingerprints. For decades, scientists called this mysterious green emission the Aurora Line, because they could not find any earthly substance that produced light at exactly that wavelength. Laboratory equipment from the early 1900s. Glass tubes and metal instruments arranged on wooden tables, glowing with experimental electric discharges. Some researchers even proposed that a new element existed only in the upper atmosphere, naming it geocoronium, after Earth's crown of light. The truth finally emerged in the 1920s when quantum physics revealed how atoms behave under extreme conditions. Oxygen atoms suspended in the near vacuum of space, their electrons jumping between energy levels as they absorb and release packets of light. Scientists realized that the mysterious green line came from ordinary oxygen, but oxygen in a state impossible to create in earthly laboratories. The thin atmosphere 60 miles above Earth, where oxygen atoms drift in near-perfect isolation, glowing green when struck by solar particles. At this altitude, oxygen atoms can stay in an excited state for several seconds before releasing their green photon, something that cannot happen at ground level, where collisions with other molecules interrupt the process instantly. The dominance of green in aurora displays reflects the perfect storm of conditions in Earth's upper atmosphere. Layers of atmosphere stacked like invisible sheets, each altitude glowing with different colors as solar particles penetrate deeper into the air. Oxygen produces green light most efficiently at altitudes between 50 and 100 miles up, exactly where the densest aurora activity occurs. Solar particles streaming toward Earth in invisible rivers, their energy perfectly matched to excite oxygen atoms in the thin upper air. Below 50 miles, the atmosphere becomes too thick for the delicate green emission to survive, while above 100 miles, there are too few oxygen atoms to create bright displays. The red oxygen line at 630 nanometers tells a different story of altitude and energy. High-altitude aurora glowing deep red against the star-filled sky. The crimson light emanating from oxygen atoms floating in the near vacuum of space. This red emission requires even more gentle conditions than green, occurring mainly above 100 miles, where oxygen atoms can remain undisturbed for minutes at a time. The transition zone between green and red aurora, where emerald curtains gradually fade to crimson wisps in the highest reaches of the atmosphere. During intense solar storms, red aurora can extend much lower, creating the rare blood-red displays that terrified ancient observers who saw them as omens of war or disaster. Nitrogen adds the blue and purple accents that frame the green displays. Nitrogen molecules glowing blue and purple at the lower edges of aurora curtains, creating delicate color gradients that shift from green to violet. Unlike oxygen's atomic emissions, nitrogen glows through molecular transitions that produce bands of color rather than single bright lines. The molecular structure of nitrogen revealed in aurora light, its chemical bonds vibrating and glowing as solar particles transfer their energy. These nitrogen emissions typically appear below 60 miles altitude, where the atmosphere becomes dense enough for molecular interactions to dominate over atomic processes. The perfect green of most aurora displays represents a cosmic coincidence of chemistry and physics. The electromagnetic spectrum revealing why human eyes see aurora green so vividly. The wavelength perfectly matched to our visual sensitivity. Human eyes evolved to be most sensitive to green light, the same color that dominates aurora emissions, making these displays appear far brighter and more vivid than they would to creatures with different vision. Aurora light interacting with the human eye, green photons striking the retina and creating the vivid emerald impressions that have inspired countless generations. This match between our biology and the physics of excited oxygen creates the stunning visual impact that has made aurora watching one of nature's most sought-after experiences. Above the familiar green curtains, where Earth's atmosphere grows impossibly thin, aurora displays reveal their most mysterious colors. Brilliant red aurora flames dancing at extreme altitude, their crimson glow stretching across the star-filled sky like ethereal fire. Red aurora occurs above 150 miles altitude, where oxygen atoms exist in such low density that they can hold their excited energy for minutes instead of seconds. Sparse oxygen atoms floating in the near vacuum of space, glowing deep red as they slowly release stored solar energy. This red emission represents forbidden light, a quantum mechanical process that can only happen in the near-perfect vacuum of space. The rarest aurora color appears as pure blue, created when sunlight itself becomes trapped within the magnetic field lines. Intense blue aurora ribbons shimmering against the black void, their electric azure light cutting through the darkness like liquid lightning. Blue aurora forms when solar particles strike nitrogen molecules at extremely high altitudes, above 100 miles. Nitrogen molecules vibrating and glowing brilliant blue in the thin upper atmosphere. Their molecular bonds energized by cosmic particle impacts. These blue displays often appear during the most powerful solar storms, when particle bombardment reaches levels that can disrupt satellite communications. Purple aurora creates perhaps the most stunning visual surprise, appearing as vertical columns that stretch from horizon to zenith. Towering purple aurora columns rising like cosmic pillars, their violet light extending from the dark horizon to the star-scattered zenith above. This color emerges from a complex dance between nitrogen and oxygen at intermediate altitudes, typically between 60 and 100 miles high, the boundary zone where Earth's atmosphere transitions from thick to thin, glowing with mixed purple light as different gases interact. Purple aurora often signals the beginning or end of major geomagnetic storms, appearing as the magnetic field reorganizes itself. The most elusive aurora color appears as pure white, visible only during the most intense solar particle events. Brilliant white aurora sheets flowing across the polar sky, their pure luminous glow outshining the surrounding stars and planets. White aurora occurs when all colors blend together at once, created by simultaneous excitation of oxygen, nitrogen, and trace atmospheric gases. Multiple atmospheric layers glowing simultaneously, their combined light creating sheets of pure white radiance against the cosmic darkness. These white displays can become so bright they cast shadows on snow-covered landscapes, turning night temporarily into an ethereal twilight. Yellow aurora represents one of nature's rarest light shows, appearing only when specific atmospheric conditions align perfectly. Golden yellow aurora waves rippling through the night sky, their warm, honey-colored light contrasting with the cold blue of distant stars. Yellow emissions come from sodium atoms deposited in the upper atmosphere by meteors that burn up during their journey to Earth. Microscopic sodium particles glowing golden yellow as solar wind particles energize them in the thin upper atmosphere. These sodium atoms typically exist at altitudes near 55 miles, creating a narrow band where yellow aurora can appear. Pink aurora adds delicate beauty to the high-altitude light show, forming when hydrogen atoms interact with the solar wind. Soft pink aurora curtains swaying gently in the magnetic field, their rose-colored light creating ethereal patterns against the star-filled void. Hydrogen emissions produce a specific shade of deep pink that appears most commonly during solar maximum periods. Hydrogen atoms in Earth's outer atmosphere glowing soft pink as they absorb and release energy from solar particles. This pink light often appears at the very top of aurora displays, creating a subtle crown above the more familiar green and red emissions. The physics behind these rare colors reveals the incredible precision of atomic energy levels. The quantum energy levels of atmospheric atoms visualized as glowing steps, each level producing its own specific color of light. Each gas in Earth's atmosphere can only emit light at very specific wavelengths, determined by the exact energy differences between electron orbits. Electron shells around oxygen and nitrogen atoms, their orbital paths glowing as electrons jump between energy levels. When solar particles provide exactly the right amount of energy, they can excite atoms to higher energy states that produce these unusual colors. The altitude where each color appears depends on atmospheric density and the energy of incoming solar particles. Earth's atmosphere shone in layers, each altitude glowing with its characteristic aurora color, from red at the top to green below. Higher energy particles penetrate deeper into the atmosphere, while lower energy particles interact with gases at greater heights. Solar particles of different energies streaming toward Earth, their paths determining which atmospheric layer will glow with aurora light. This creates a natural sorting system where the most energetic displays show the full spectrum of aurora colors, arranged by altitude. Temperature plays a surprising role in determining which rare colors appear during aurora displays. The thermosphere glowing with aurora light, its extreme temperatures affecting how atmospheric gases respond to solar particle bombardment. At aurora altitudes, atmospheric temperature can reach over 1,000 degrees Celsius, hot enough to change how atoms and molecules behave. Superheated atmospheric gases glowing with aurora light, their high temperature allowing for rare quantum transitions that produce unusual colors. These extreme temperatures help explain why some aurora colors only appear during the most intense geomagnetic storms. When solar energy heats the upper atmosphere to extraordinary levels. The extreme temperatures that create rare aurora colors also trigger responses throughout Earth's living systems. The Arctic tundra, stretching endlessly under shimmering green aurora curtains, the frozen landscape bathed in ethereal light. Many animals in polar regions have evolved to use aurora displays as navigation aids during the long winter months. Caribou herds migrate across vast distances, and scientists believe these animals can sense the magnetic field changes that accompany aurora activity. Snow-covered mountains beneath dancing aurora ribbons, the peaks glowing softly in the reflected green light. The same magnetic disturbances that create the northern lights affect the inner compass that guides migrating birds across thousands of miles. Whales swimming in Arctic waters experience the aurora's influence in ways we are only beginning to understand. Icy Arctic waters reflecting aurora light, the surface rippling with green and blue reflections from the sky above. The magnetic field fluctuations that accompany geomagnetic storms can disrupt the navigation systems that whales use for their epic journeys between feeding and breeding grounds. Some whale species change their migration timing during periods periods of intense aurora activity. Frozen Arctic coastline under brilliant aurora displays. Ice formations glowing with reflected light in shades of green and blue. This connection shows how solar storms that begin 93 million miles away can influence the behavior of Earth's largest creatures. The aurora's magnetic effects reach deep into the ocean itself. Ocean currents flowing beneath polar ice, the water glowing faintly with bioluminescent organisms responding to magnetic changes. Earth's magnetic field, which creates the aurora, also influences the movement of ocean currents that carry nutrients and heat around the globe. When solar storms intensify aurora displays, they also create small but measurable changes in ocean circulation patterns. Deep ocean trenches where magnetic minerals settle, creating patterns on the seafloor that record ancient aurora activity. Marine organisms that navigate using magnetic fields can become disoriented during strong geomagnetic storms. The same events that produce the most spectacular aurora shows. The connection between aurora activity and Earth's climate operates on multiple time scales. Atmospheric layers glowing with aurora light, each altitude showing different responses to solar particle bombardment. During periods of high solar activity, when aurora displays become more frequent and intense, the upper atmosphere heats up and expands. This expansion affects satellite orbits and also influences weather patterns in the lower atmosphere. The ionosphere glowing with aurora light, its charged particles creating invisible connections between Earth's surface and space. Scientists have discovered that strong aurora events can trigger changes in atmospheric circulation that affect weather systems thousands of miles away from the polar regions. The aurora's influence extends to the smallest organisms on Earth. Microscopic plankton in polar waters, their bioluminescent glow mixing with aurora reflections on the ocean surface. Bacteria and other microorganisms that live in extreme polar environments show changes in their activity levels during aurora events. The electromagnetic radiation associated with aurora displays can affect the chemical processes that these tiny life forms use to survive in in harsh conditions. Polar ice crystals forming intricate patterns, each crystal reflecting and refracting aurora light into rainbow spectrums. Some bacteria actually increase their reproduction rates during geomagnetic storms, suggesting they have evolved to take advantage of the energy changes that accompany aurora activity. Plants in polar regions also respond to the aurora's electromagnetic effects. Arctic vegetation covered in frost, the plants glowing softly under the green light of aurora curtains overhead. The same magnetic field changes that create aurora displays can influence the growth patterns of mosses and lichens that survive in polar climates. These hardy plants show seasonal variations that correlate with aurora activity levels throughout the year. Tundra landscape under swirling aurora displays, the ground vegetation creating patterns that mirror the light dancing overhead. The connection between solar activity and plant growth demonstrates how energy from our star influences life on Earth through multiple pathways. Even the timing of aurora displays connects to biological rhythms across the planet. The Arctic horizon glowing with aurora light, the boundary between Earth and space shimmering with electromagnetic energy. The 11-year solar cycle that controls aurora frequency also influences migration patterns, breeding cycles, and population dynamics in species ranging from Arctic foxes to Antarctic penguins. Polar regions during the long winter night, aurora light providing the only illumination across vast expanses of ice and snow. This shows how the sun's magnetic heartbeat creates rhythms that pulse through Earth's entire web of life, connecting the smallest bacteria to the largest whales through the beautiful dance of aurora light. Long before scientists understood magnetic fields and solar particles, indigenous peoples across the Arctic watched the dancing lights with deep reverence and careful observation. Ancient tundra landscape under brilliant aurora curtains, the light reflecting off pristine snow and ice formations stretching to the horizon. The Inuit called them Axarniat, believing the lights were spirits of the dead playing a ball game with a walrus skull. This wasn't mere superstition. but a sophisticated way of understanding patterns in the sky that connected to seasonal changes and weather forecasts. Traditional Arctic settlement area with aurora light illuminating the natural landscape, showing how indigenous peoples lived in harmony with these celestial displays. The Sami people of northern Scandinavia named the aurora revanchelet, meaning fox fires. Their stories described a magical fox running so fast across the snow that its tail brushed crystals into the air, creating sparks that lit up the heavens. Snowy Arctic terrain under swirling green and purple aurora, the landscape appearing to glow from within as the lights dance overhead. These tales encoded practical knowledge about aurora timing and intensity that helped communities prepare for harsh weather patterns. Native Alaskan tribes developed detailed vocabularies for different types of aurora displays. Vast polar wilderness with aurora bands stretching across the entire sky, creating natural light patterns that indigenous peoples used for navigation and timekeeping. They recognized that certain aurora shapes predicted storms, while others signaled clear weather ahead. The Cree called them the dance of the spirits, understanding that the lights appeared more frequently during certain moon phases and seasonal transitions. Remote Arctic valley with aurora light creating ethereal reflections on frozen lakes and streams, showing the intimate connection between sky and earth. These indigenous observations, passed down through thousands of years of oral tradition, contain remarkably accurate information about aurora behavior that modern science has only recently confirmed. The stories encoded the 11-year solar cycle, the seasonal patterns of geomagnetic activity, and the relationship between aurora displays and atmospheric conditions. Traditional hunting grounds under spectacular aurora displays, the natural world illuminated by the interplay of magnetic fields and solar wind. Many Arctic cultures developed ceremonies and rituals timed to aurora appearances, recognizing that these lights marked important transitions in the natural world. The timing of these ceremonies often coincided with peak aurora activity periods that we now know correspond to solar maximum phases. Ancient migration routes across polar regions, aurora light guiding the way through landscapes that have remained unchanged for millennia. The Inuit understood that aurora intensity connected to animal behavior, noting that caribou migrations and seal movements changed during periods of frequent light displays. This knowledge helped them predict the best hunting and fishing times throughout the year. Sacred sites in the Arctic, where indigenous peoples gathered to observe aurora, the natural amphitheaters carved by glaciers and illuminated by celestial light. The Greenlandic Inuit called particularly bright displays Arsarnarit, recognizing them as messages from ancestors about upcoming weather changes. Their detailed observations of aurora colors and movements provided early warning systems for dangerous storms that could threaten survival in harsh polar conditions. Traditional seasonal camps positioned to take advantage of aurora viewing, showing how indigenous peoples integrated these displays into their understanding of natural cycles. The Ojibwe people called the Northern Lights Geobayag, meaning the spirits of the north, and understood their connection to the changing seasons and the health of the land. These stories preserved knowledge about how solar activity influences everything from plant growth to animal reproduction cycles. Ancient storytelling circles under aurora light, the natural world serving as both classroom and cathedral for indigenous knowledge systems. The Menominee recognized that aurora displays followed patterns connected to the phases of the moon and the position of certain stars, encoding astronomical knowledge that helped them track seasonal changes with remarkable precision. Remote wilderness areas where indigenous peoples developed their deep understanding of aurora patterns, the landscape unchanged since the last ice age. Today, climate scientists work with indigenous elders to understand how aurora patterns have shifted over generations, recognizing that traditional knowledge contains centuries of careful observation about these celestial displays. Traditional hunting and fishing areas under aurora light, showing how indigenous peoples integrated celestial observations with practical survival skills. The Yupik people of Alaska called the lights Aksarniit and understood their connection to the spirits of sea mammals, encoding knowledge about how geomagnetic activity influences ocean currents and marine life, behavior, sacred mountains and valleys, where indigenous ceremonies took place under aurora displays, the natural world serving as a living temple. These traditional knowledge systems recognized that aurora activity connects to broader patterns in the natural world, from weather systems to animal migrations to plant growth cycles. The stories preserved this understanding across generations, maintaining a holistic view of how earth and sky work together. Ancient travel routes through polar regions, aurora light providing navigation aids that indigenous peoples used for thousands of years. The Netsilik Inuit understood that certain aurora formations predicted the arrival of specific weather patterns, knowledge that proved essential for survival in one of Earth's most challenging environments. Traditional seasonal gathering places under spectacular aurora displays, showing how indigenous communities organized their lives around natural cycles. Modern research confirms that many indigenous observations about aurora timing and intensity were remarkably accurate, demonstrating sophisticated understanding of the connections between solar activity, magnetic fields, and atmospheric conditions. Remote Arctic landscapes, where indigenous knowledge keepers continue to observe aurora patterns, maintaining traditions that stretch back thousands of years. The wisdom encoded in these ancient stories reveals that aurora displays have remained remarkably consistent over centuries, following the same solar cycles and seasonal patterns that indigenous peoples learned to read like a calendar written across the sky. The aurora creates more than just visible light dancing across the polar skies. Shimmering curtains of green and purple aurora light stretching across a star-filled Arctic night. Radio waves invisibly pulsing through the glowing atmosphere. These same charged particles that paint the night also generate radio waves, creating a symphony of electromagnetic signals that scientists can detect and study. The aurora literally sings in frequencies we cannot hear, but our instruments can capture. Massive solar wind streams flowing toward Earth's magnetic field. Invisible radio frequencies rippling through the cosmic plasma like waves on an ocean. When solar particles collide with our atmosphere, create what researchers call auroral kilometric radiation. This radio emission travels at the speed of light, reaching frequencies between 50 and 500 kilohertz. Earth's magnetosphere glowing with invisible radio energy. The planet surrounded by a bubble of electromagnetic activity that pulses with auroral rhythms. The intensity of these radio signals directly matches the brightness of the visible aurora, creating a perfect harmony between what we see and what radio telescopes detect. Towering aurora columns reaching hundreds of kilometers into space, each glowing pillar generating its own unique radio signature that scientists can map and measure. The radio waves follow the same magnetic field lines that guide the visible light displays. Scientists discovered that different types of aurora produce distinct radio patterns. Spiral formations of aurora light dancing above polar ice fields. Radio waves spiraling along the same magnetic pathways that shape the visible curtains. Discrete aurora arcs generate steady radio tones, while flickering aurora creates rapid bursts of radio noise. The northern polar region viewed from high above, showing how radio wave patterns mirror the oval shape of the aurora zone around the magnetic pole. These radio emissions help researchers understand aurora behavior, even when clouds block the visible display. Radio telescopes can detect aurora activity during daylight hours when the human eye cannot see the faint glow against the bright sky. Daylight aurora glowing faintly above snow-covered mountains, invisible to human eyes, but clearly detectable through radio wave emissions. This allows scientists to study aurora patterns continuously, building a complete picture of how solar activity affects our planet. Jupiter's massive aurora rings glowing around its polar regions. The giant planet generating radio signals thousands of times stronger than Earth's auroral emissions. Other planets with magnetic fields also produce auroral radio waves. Jupiter creates the most powerful auroral radio emissions in our solar system, so intense that amateur radio operators on Earth can sometimes detect them. Saturn's ethereal aurora, crowns shimmering at both poles. The ringed planet's magnetic field generating delicate radio harmonics that spacecraft can record. These planetary radio signatures help scientists understand how different magnetic field strengths and atmospheric compositions affect aurora formation. Ancient radio waves from distant auroral displays traveling through interplanetary space, carrying information about solar storms that occurred years ago. The radio waves from aurora can travel vast distances through space before fading. Some of these signals bounce off the ionosphere and return to Earth, creating echoes that reveal the height and density of different atmospheric layers. Earth's ionosphere glowing with aurora activity, radio waves bouncing between atmospheric layers like light reflecting in a hall of mirrors. Radio operators have learned to use aurora-reflected signals to communicate across distances that would normally be impossible. Brilliant aurora displays creating natural radio interference patterns. The electromagnetic activity disrupting communication signals across polar regions. Strong aurora events can interfere with radio communications, GPS systems, and power grids. The same beautiful light show that captivates observers also generates electromagnetic pulses powerful enough to affect technology across entire continents. Power lines stretching across aurora-lit landscapes. The dancing lights above creating invisible electromagnetic fields that can surge through electrical systems. Understanding auroral radio emissions helps engineers design systems that can withstand these natural electromagnetic storms. Research stations nestled in polar valleys, their radio antennas pointed skyward to capture the subtle electromagnetic songs of dancing aurora overhead. Modern radio astronomy reveals that each aurora display has its own unique electromagnetic fingerprint. Scientists can identify different types of solar-wind interactions by analyzing the radio patterns they create. Vast arrays of radio telescopes scanning the aurora-filled sky, each dish capturing different frequencies of the electromagnetic symphony playing overhead. This radio data, combined with visual observations, creates the most complete understanding we have ever had of how our planet responds to the constant flow of energy from our star. This radio data, combined with visual observations, creates the most complete understanding we have ever had of how our planet responds to the constant flow of energy from our star. Scientists can now predict when aurora displays will appear with remarkable accuracy. Computer screens glowing with colorful solar wind data streams, magnetic field measurements flowing across monitors in research stations beneath star-filled polar skies. Space weather forecasters track solar flares and coronal mass ejections as they travel the 93 million miles from Sun to Earth. These predictions help photographers, tourists, and researchers plan their aurora viewing expeditions. The journey from solar storm to visible aurora takes between 1 and 3 days. Brilliant solar flares erupting from the sun's surface, streams of charged particles racing outward through the dark void toward distant planets. Satellites positioned between Earth and the Sun act as early warning systems. They measure the speed and density of approaching solar wind. Metallic satellites drifting in the black space between Earth and Sun. Their solar panels catching starlight as they monitor invisible particle streams. When these instruments detect a strong solar wind pulse, aurora alerts go out to observers around the world. Ground-based magnetometers detect the subtle changes in Earth's magnetic field that happen before aurora displays begin. Sensitive magnetic field detectors buried in snowy polar landscapes, their readings fluctuating as invisible magnetic waves ripple through the planet. These instruments can sense magnetic disturbances hours before the first green curtains appear in the sky. The magnetic field lines compress and stretch like invisible rubber bands. Earth's magnetic field lines bending and warping around the planet. Invisible forces creating curved pathways for solar particles to follow toward the poles. Scientists watch these magnetic signatures the way meteorologists watch approaching storm clouds. Aurora prediction models combine satellite data, magnetic field measurements, and solar observations into detailed forecasts. Vast computer visualization systems displaying Earth's magnetic field as glowing lines of force, solar wind particles streaming toward the polar regions in brilliant colors. These models can predict not just when aurora will appear, but how bright they will be and how far south they might extend. Strong geomagnetic storms can push aurora displays hundreds of miles closer to the equator than usual. Aurora displays stretching unusually far south. Green and purple lights dancing over landscapes that rarely see such celestial shows. During the most powerful solar storms, people in places like New York or London might glimpse the northern lights on their horizon. The prediction accuracy has improved dramatically over the past 2 decades. Research stations scattered across the Arctic tundra, their instruments continuously measuring the invisible electromagnetic environment beneath dancing aurora. Modern forecasts can predict aurora activity up to 3 days in advance with reasonable accuracy. Short-term predictions covering the next few hours are often remarkably precise. Real-time aurora monitoring stations positioned across northern Canada and Alaska, their sensors tracking the exact moment when solar particles begin interacting with the upper atmosphere. This precision helps aurora photographers know exactly when to set up their cameras and where to point them. The sound of aurora prediction comes from the constant hum of data flowing between satellites, ground stations, and research centers. Streams of data flowing invisibly through the atmosphere, connecting polar research stations with satellites orbiting high above the aurora zone. Radio telescopes capture the electromagnetic songs that aurora create. These signals can be converted into audio frequencies that humans can hear. Radio waves from aurora displays converted into sound, creating ethereal musical tones that rise and fall like cosmic wind chimes in the darkness. The aurora's radio signature sounds like whistling wind mixed with electronic music. Each type of aurora activity creates its own distinctive audio pattern. Scientists have learned to recognize the radio fingerprints of different aurora types. Spectrographic displays showing aurora radio emissions as cascading waterfalls of color, each frequency creating its own unique pattern in the electromagnetic spectrum. Pulsating aurora create rhythmic radio bursts. Flickering aurora generate rapid-fire electromagnetic pulses. Pulsating aurora creating rhythmic patterns of light and electromagnetic energy. The regular beats visible both in the sky and on sensitive radio equipment. Steady aurora arcs produce continuous radio tones. These audio signatures help researchers understand exactly what processes are happening hundreds of miles overhead. The electromagnetic environment around Earth changes constantly as solar wind conditions shift. Earth's magnetosphere rippling and fluctuating like an invisible ocean. Solar wind particles creating waves and currents in the planet's magnetic field. Sensitive instruments detect these changes in real time. The data flows to prediction centers where computers calculate the probability of aurora activity. Global networks of magnetic field sensors, creating an invisible web of monitoring stations, each one contributing data to the worldwide aurora prediction system. This network of sensors and satellites creates a comprehensive picture of space, weather conditions around our planet. Aurora forecasting has become as sophisticated as terrestrial weather prediction. Detailed space weather maps showing solar wind conditions across the solar system. Earth positioned in the flowing streams of particles from the distant sun. Scientists track solar storms the way meteorologists track hurricanes. The most intense geomagnetic storms receive classifications similar to hurricane categories. Massive geomagnetic storms surrounding Earth, the planet's magnetic field glowing with intense activity as powerful solar winds create spectacular aurora displays. These storm predictions help power companies prepare their electrical grids for potential disruptions. They also help aurora enthusiasts plan their viewing adventures. The accuracy of these predictions continues to improve as scientists gather more data about the complex interactions between solar wind and Earth's magnetic field. Aurora research continuing around the clock. Scientists in polar regions studying the endless dance between our planet and the solar wind streaming from our star. Each aurora display teaches researchers something new about the delicate balance between Earth and space. The mathematics of aurora formation reveals patterns as elegant as any equation in physics. Precise geometric patterns of light dancing across the polar sky, mathematical curves and spirals forming in the glowing green aurora curtains. Scientists measure aurora activity at different altitudes with remarkable precision. The lowest aurora displays begin around 60 miles above Earth's surface. Layered atmospheric zones stretching upward from Earth, each altitude glowing with different colored aurora light, creating distinct bands of luminous activity. This altitude marks where Earth's atmosphere becomes thin enough for solar particles to penetrate deeply. The relationship between altitude and color follows strict mathematical rules. Vertical columns of aurora light extending from 60 miles to over 400 miles high, each altitude band glowing with its characteristic color. Green aurora peaks at exactly 62 miles above ground. This precise height represents the optimal density for oxygen atoms to emit their signature green wavelength. Brilliant green aurora curtains concentrated at the 62-mile altitude mark, the most intense glow occurring at this mathematically perfect height. Red aurora appears much higher, typically above 150 miles. The mathematics here involves atmospheric density decreasing exponentially with altitude, exponential curves showing how Earth's atmosphere thins with increasing altitude. The mathematical relationship governing where different aurora colors can form. At higher altitudes, oxygen atoms have more time between collisions. This extra time allows them to emit red light instead of green. Sparse high-altitude regions where oxygen atoms drift freely, glowing red as they slowly release energy from solar particle impacts. The blue and purple colors of nitrogen follow their own altitude rules. Nitrogen glows blue below 60 miles and purple above 80 miles. Deep blue nitrogen, aurora flickering at the lower edges of the atmosphere, where air density reaches its mathematical threshold for blue light emission. The energy calculations behind aurora formation involve precise measurements. Solar particles streaming toward Earth, carrying exact amounts of kinetic energy. Each particle following predictable mathematical trajectories. A single solar proton carries about 1,000 electron volts of energy. When millions of these particles strike atmospheric atoms simultaneously, the total energy release becomes measurable. Cascading energy transfers as solar particles collide with atmospheric atoms. Each collision following the mathematical laws of momentum and energy conservation. Scientists calculate that a typical aurora display releases energy equivalent to several nuclear power plants. The geometry of Earth's magnetic field creates mathematical relationships that determine aurora placement. Earth's magnetic field lines forming precise geometric curves that guide solar particles toward the polar regions in mathematically predictable patterns. The magnetic field strength decreases with distance, following an inverse square law. This mathematical relationship explains why aurora activity concentrates in oval zones around the magnetic poles. Oval-shaped aurora zones centered on Earth's magnetic poles. The mathematical precision of these regions determined by magnetic field geometry. The aurora oval expands and contracts based on solar wind pressure, following equations that space physicists can calculate in advance. Mathematical models showing how the aurora oval changes size and position based on solar wind conditions. Precise calculations predicting the movement of these glowing regions. During quiet solar conditions, the aurora oval measures about 15 degrees wide. Strong geomagnetic storms can expand this oval to 30 degrees or more, expanding rings of aurora activity growing outward from the magnetic poles. The mathematical relationship between solar wind strength and aurora oval size. The expansion follows logarithmic scaling laws that allow scientists to predict exactly how far south aurora will be visible. Temperature measurements reveal another mathematical pattern in aurora formation. Temperature gradients in the upper atmosphere, creating distinct zones where different aurora processes occur. Each temperature range following mathematical laws. thermosphere, where most aurora occur, reaches temperatures of over 3,000 degrees Fahrenheit. Despite this extreme heat, the air density remains so low that a human would freeze instantly. The paradox of the hot but sparse thermosphere, where mathematical relationships between temperature and density create the perfect conditions for aurora formation. This mathematical paradox occurs because temperature measures the speed of individual atoms, while heat transfer requires many atoms working together. Precise measurements of particle velocities and collision rates in the thermosphere, the mathematical foundation underlying all aurora phenomena. The collision frequency between atmospheric atoms decreases exponentially with altitude. This mathematical relationship determines exactly where each color of aurora can form and how long it will last. Exponential decay curves showing how atmospheric collision rates change with altitude. The mathematical beauty underlying the aurora's colorful displays. Each aurora display represents millions of these mathematical relationships working together in perfect harmony. The aurora exists because of an almost impossible balance of conditions that took billions of years to create. Earth suspended in the perfect zone around the sun, bathed in golden light, the precise distance that allows liquid water and magnetic fields to flourish. Our planet sits exactly 93 million miles from the sun. Move us just 5% closer, and our atmosphere would boil away like Venus. The thin blue shell of Earth's atmosphere glowing against the black void of space, a fragile barrier protecting all life below. Move us 5% farther out, and we would freeze solid like Mars. This delicate positioning creates the perfect conditions for our magnetic field to interact with solar wind. Invisible magnetic field lines streaming from Earth's poles, creating a protective bubble around the planet in the darkness of space. The magnetic field itself depends on our planet's molten iron core, spinning at exactly the right speed. Too slow, and the field weakens. The glowing molten core of Earth, visible through a cross-section. Swirling currents of liquid iron, generating the magnetic dynamo. Too fast, and it becomes chaotic and unstable. Our atmosphere maintains the precise density needed for aurora formation through an intricate dance of temperature and pressure. Layers of atmosphere stacked like translucent sheets, each glowing with different colors as they stretch toward space. The thermosphere, where aurora dance, contains exactly the right mix of oxygen and nitrogen atoms. Individual atoms of oxygen and nitrogen floating in the sparse upper atmosphere, glowing green and red when struck by solar particles. Change this mixture by even a small percentage, and the colors would shift dramatically. The thickness of our atmospheric layers follows mathematical relationships that have remained stable for millions of years. Precise atmospheric layers visible from space, each zone maintaining its exact altitude through gravitational and thermal balance. The troposphere extends exactly 11 miles up. The stratosphere reaches 31 miles. The boundary between atmospheric layers glowing softly, where temperature gradients create distinct zones in the twilight sky. These boundaries exist because gravity and temperature create natural stopping points where air density changes rapidly. Weather patterns on Earth's surface influence aurora formation in ways scientists are still discovering. Massive storm systems swirling across continents, their energy reaching up through the atmosphere toward space. Large thunderstorms can actually push the boundary between atmospheric layers higher, changing where aurora form. Lightning illuminating storm clouds from within. Electrical energy connecting Earth's surface to the upper atmosphere. The jet stream, that river of fast-moving air 6 miles above us, affects how solar particles penetrate our magnetic field. Ocean currents regulate global temperatures with mathematical precision, maintaining the atmospheric conditions that make aurora possible. Vast ocean currents flowing across the planet like glowing rivers, carrying heat from equator to poles in endless circulation. The Gulf Stream alone transports as much energy as 1 million power plants. Warm ocean waters glowing with bioluminescent life. The thermal energy that drives global weather patterns. Without these currents, the temperature differences between Earth's regions would be too extreme for stable aurora zones. Even the tilt of our planet plays a role in aurora formation. Earth tilted at its perfect 23-degree angle, creating the seasonal changes that affect magnetic field interactions. This 23-degree tilt creates our seasons and determines how solar wind hits our magnetic field throughout the year. The changing angle of sunlight across Earth's surface as the planet orbits, creating the seasonal aurora patterns. A different tilt would shift the aurora zones to completely different latitudes. The moon's gravitational pull helps stabilize this delicate system by preventing our planet's tilt from wobbling too much. The moon hanging in space near Earth, its gravitational influence maintaining the planet's stable rotation and tilt. Without our unusually large moon, Earth would tumble chaotically, and the aurora zones would shift unpredictably. Tidal forces between Earth and moon, visible as subtle distortions in both bodies. The gravitational dance that maintains stability. The aurora we see tonight exists because countless variables have remained in perfect balance for eons. The complete Earth-Moon-Sun system in harmony. 3 celestial bodies whose precise relationships create the conditions for aurora to dance across polar skies. Yet, for all our scientific understanding, the aurora still holds secrets that puzzle researchers today. A brilliant green aurora curtain rippling across the night sky, its edges flickering and dancing with mysterious patterns that scientists cannot fully explain. The most basic question remains surprisingly difficult to answer. Why does the aurora look so different to cameras than to our eyes? The same aurora viewed through different wavelengths of light, revealing hidden colors and structures invisible to human vision. Our eyes see gentle green curtains swaying in the darkness, but cameras capture vivid purples, blues, and reds that we cannot perceive in real time. This difference goes beyond simple light sensitivity. The human eye's structure magnified, showing the rods and cones that detect different wavelengths of aurora light. Scientists know that our eyes adapt to darkness differently than camera sensors, but the exact mechanisms remain unclear. Aurora light particles striking the retina, creating the electrical signals that become our perception of the dancing lights. The brain processes aurora light in ways we do not fully understand. Some people report seeing colors that should be impossible given the known wavelengths of aurora emissions. Mysterious pink and violet aurora bands weaving through the more common green. Colors that appear only under specific atmospheric conditions. The aurora's movement patterns also defy complete explanation. Aurora curtains suddenly brightening and dimming in waves. The light pulses traveling along invisible magnetic field lines. Researchers can predict when an aurora will appear, but they cannot predict exactly how it will dance. Rapid flickering movements within aurora bands, like cosmic fire burning in the upper atmosphere. The lights sometimes pulse in rhythm, sometimes flow like water, sometimes explode outward in sudden bursts. An aurora substorm beginning, with bright rays suddenly shooting upward from the horizon like searchlights piercing the darkness. Each display follows its own mysterious choreography. Even more puzzling are the sounds some people claim to hear during intense aurora displays. Silent aurora ribbons stretching across a star-filled sky, their ethereal glow reflecting off snow-covered mountains below. For centuries, witnesses have described crackling, hissing, or whooshing sounds accompanying bright auroras, sound waves visualized as ripples in the air. Though scientists debate whether aurora truly creates audible sounds, scientists remain divided about whether these sounds are real or imagined. The thin atmosphere at aurora altitudes, too sparse to carry traditional sound, waves down to Earth's surface. Some researchers propose that electromagnetic fields from intense auroras might create sounds by interacting with objects on the ground. The connection between aurora activity and animal behavior presents another unsolved puzzle. Migrating birds flying beneath a glowing aurora, their navigation systems potentially affected by the magnetic disturbances. Many indigenous cultures describe animals acting strangely during aurora displays. But modern science has found little concrete evidence. Reindeer grazing peacefully under dancing northern lights, seemingly unaffected by the cosmic light show above. Some studies suggest that magnetic field changes during aurora events might affect animal navigation, but the data remains inconclusive. Whales swimming beneath ice, while aurora light reflects off the frozen surface above. Two natural phenomena sharing the same polar environment. Perhaps the deepest mystery involves the aurora's role in Earth's larger systems. Aurora light connecting the upper atmosphere to the magnetosphere. Invisible energy flows, linking Earth's surface to space. Scientists know that aurora activity affects radio communications and satellite operations, but they do not fully understand all the connections. Electromagnetic energy cascading down through atmospheric layers, each altitude responding differently to the aurora's influence. The aurora might influence weather patterns in ways we have not yet discovered. High altitude winds swirling around aurora zones, potentially affecting the jet stream and global weather systems. Some researchers suspect that major aurora events could trigger changes in atmospheric circulation. But proving these connections requires decades of careful observation. The aurora continues to surprise us with displays that do not fit our current models. Rare red aurora bands glowing at extreme altitudes, far higher than the typical green curtains of lower atmosphere. Occasionally, auroras appear at latitudes where they should be impossible, or display colors that existing theory cannot explain. Unexpected aurora formations spiraling in perfect circles, geometric patterns that challenge our understanding of magnetic field behavior. These anomalies remind us that despite centuries of study, the aurora still holds secrets waiting to be discovered. The entire aurora oval glowing around Earth's magnetic pole. A perfect ring of light marking the boundary between our planet and the cosmos. The future holds remarkable changes for the Aurora Borealis, driven by our sun's own evolution. The sun, blazing with intense solar flares, erupting from its surface, massive streams of charged particles racing toward Earth through the darkness of space. As our star ages over the next billion years, it will gradually grow brighter and more active. This increased solar output will create more frequent and intense geomagnetic storms, Earth's magnetosphere glowing brilliantly as it deflects powerful solar winds. The protective magnetic field lines stretching far into space like luminous ribbons. The aurora displays of the distant future may stretch much farther south than they do today, painting skies over regions that have never seen the northern lights. Solar storms will become more spectacular as the sun enters different phases of its life cycle. Massive coronal mass ejections spiraling away from the sun's surface, billion-ton clouds of plasma traveling at millions of miles per hour through the solar system. These future storms could trigger aurora displays visible from the equator, turning the entire night sky into a canvas of dancing light. The entire Earth surrounded by a shimmering aurora shell. Green and red curtains of light wrapping around the planet like a glowing cocoon. Scientists predict that some of these storms will be powerful enough to create aurora colors we have never seen before, as different atmospheric gases respond to the increased energy. The sun's magnetic field will also change dramatically over cosmic time scales. The sun's magnetic field lines twisting and reconnecting in complex patterns, creating brilliant loops of plasma that arch high above the solar surface. These changes will alter how solar particles interact with Earth's magnetosphere, potentially creating entirely new types of aurora phenomena. Aurora curtains rippling across the sky in perfect waves, each fold catching starlight and reflecting it back in shades of blue and violet. Future aurora displays might pulse in rhythm with the sun's changing magnetic heartbeat, creating synchronized light shows across the entire polar region. Climate change will also influence how we experience future auroras. Ice crystals floating high in Earth's atmosphere, each one catching and scattering the green glow of aurora light like tiny prisms. As atmospheric composition shifts, the colors and intensity of aurora displays may change in unexpected ways. high-altitude clouds illuminated from above by aurora light, creating ethereal layers of glowing mist against the star-filled sky. Warmer polar regions might have different atmospheric conditions that could enhance or diminish certain aurora colors, while bringing out others we rarely see today. Over millions of years, Earth's magnetic field will continue its slow wandering across the planet's surface. Earth's magnetic field lines slowly shifting position, the aurora oval drifting across continents as the magnetic poles migrate through geological time. The aurora zones will move with these magnetic changes, bringing the northern lights to new regions while leaving others in darkness. Ancient mountain ranges silhouetted against brilliant aurora displays, peaks that will witness countless generations of dancing lights across deep time. Future civilizations might see aurora displays over tropical forests or desert landscapes, places where the lights have never danced before. The sun itself faces an even more dramatic future transformation. The aging sun expanding into a red giant star, its outer layers glowing deep orange and red as they stretch toward the inner planets. In about 5 billion years, our star will begin expanding into a red giant, fundamentally changing the solar wind that creates auroras. Streams of stellar material flowing away from the expanded sun, creating aurora displays of unimaginable intensity and beauty across Earth's transformed atmosphere. These final aurora displays will be unlike anything in Earth's history, as the dying sun sends waves of energy that will light up our entire atmosphere in brilliant, ever-changing colors. Even as our sun fades, new stars will be born throughout the galaxy. Young blue stars blazing with intense light in distant star-forming regions. Their stellar winds creating aurora displays on countless worlds orbiting in the cosmic darkness. Planets around these new stars will develop their own magnetic fields and atmospheres, creating aurora displays that mirror Earth's ancient light shows, nebulae glowing with the light of newborn stars. Vast clouds of gas and dust, illuminated in brilliant reds, blues, and greens across the galaxy. The aurora phenomenon will continue throughout the universe, connecting worlds across space and time endless symphony of magnetic fields, stellar winds, and dancing light. Earth's aurora displays are just one note in a vast cosmic symphony that plays across countless worlds throughout the universe. Jupiter's massive form floating in space, its thick atmosphere glowing with brilliant aurora rings around both magnetic poles, the light far more intense than Earth's displays. Jupiter's auroras shine 100 times brighter than our northern lights, powered by the giant planet's incredibly strong magnetic field, and the volcanic moon, Io's constant stream of sulfur particles. Io's volcanic surface, erupting with towering plumes of sulfur and gas. The yellow and orange material streaming away toward Jupiter in invisible magnetic field lines. These particles spiral along Jupiter's magnetic field lines, creating aurora displays that never stop, painting the gas giant's polar regions in permanent curtains of blue and ultraviolet light. Saturn hosts its own aurora shows, though they appear quite different from Earth's green curtains. Saturn's golden rings catching sunlight, while aurora displays dance around the planet's hexagonal North Pole. The six-sided storm pattern glowing with ethereal blue light. The ringed planet's auroras often form perfect circles around each pole, created by solar wind particles and material from Saturn's icy moons. Enceladus spraying geysers of water ice high above its frozen surface. The crystalline particles catching starlight as they arc through space toward Saturn. These water particles contribute to Saturn's aurora displays, connecting the small moon to its giant parent planet through invisible threads of magnetism and light. Even distant Uranus and Neptune, those ice giants at the edge of our solar system, create their own aurora displays. Uranus tilted on its side in the outer solar system, its pale blue-green atmosphere glowing with faint aurora displays around its unusual magnetic poles. Uranus spins on its side, so its auroras appear in strange locations compared to other planets, sometimes shining near the planet's equator rather than its poles. Neptune's deep blue atmosphere swirling with massive storm systems, while aurora displays flicker around the planet's magnetic field lines in the cold darkness of the outer solar system. These distant worlds receive very little energy from the sun, yet they still manage to create beautiful light displays when solar wind particles interact with their magnetic fields. Beyond our solar system, astronomers have discovered that many other stars produce stellar winds far more powerful than our sun's gentle breeze. A red dwarf star glowing dimly in space, surrounded by several rocky planets orbiting close to the small star's faint light. Red dwarf stars, the most common type in our galaxy, often produce intense flares and stellar winds that would create spectacular aurora displays on any planets with magnetic fields. Brilliant flares erupting from a red dwarf surface, streams of charged particles racing outward toward nearby planets in waves of invisible energy. Planets orbiting these active stars might experience aurora displays that cover their entire sky, turning night into a constantly shifting canvas of colored light. Some exoplanets orbit so close to their stars that they experience stellar winds thousands of times stronger than Earth's solar wind. A rocky exoplanet orbiting extremely close to its orange star. The planet's entire atmosphere glowing with intense aurora displays that never fade. These hot planets, called hot Jupiters when they're gas giants, likely have aurora displays that dwarf anything in our solar system. A gas giant planet with swirling cloud bands, its entire atmosphere lit up with aurora displays in brilliant reds, blues, and greens as it orbits close to its parent star. The aurora displays on these worlds might be so intense that they heat the planet's atmosphere, creating weather patterns unlike anything we see on Earth. Scientists believe that planets around binary star systems, where two stars orbit each other, might experience the most complex aurora displays in the universe. Two stars orbiting each other in a brilliant dance. Their combined stellar winds creating complex magnetic field interactions in the space between them. A planet orbiting such a system would receive stellar wind from both stars, creating aurora patterns that shift and change as the stars move in their orbital dance. A planet with twin aurora displays dancing across its atmosphere. One set of lights responding to each star in the binary system, creating intricate patterns of overlapping colored curtains. These double aurora displays would create light shows of incredible complexity, with patterns that might never repeat exactly the same way twice. Even planets without magnetic fields can create aurora-like displays when stellar winds interact directly with their atmospheres. Mars glowing with faint aurora patches scattered across its thin atmosphere. The red planet's ancient magnetic field remnants, creating isolated pockets of dancing light. Mars occasionally shows small aurora displays where ancient magnetic rocks in its crust interact with solar wind particles. Venus shrouded in thick clouds, its upper atmosphere occasionally glowing with faint aurora displays, where solar wind particles penetrate the planet's dense atmospheric layers. Venus, despite having no magnetic field, sometimes creates weak aurora displays when solar wind particles interact directly with its thick atmosphere. Throughout our galaxy, countless worlds orbit stars of every type and size, each potentially creating its own unique version of the aurora phenomenon. A massive blue supergiant star blazing with intense light. Its powerful stellar winds racing outward toward distant planets in streams of charged particles. Blue giant stars produce stellar winds so powerful that planets orbiting them might have aurora displays visible even during their daytime hours. An ancient red giant star with its outer layers expanding slowly into space, creating gentle aurora displays on planets orbiting in the star's extended atmosphere. As stars age and change, the aurora displays on their planets change too, creating an ever-evolving light show that spans billions of years. The aurora phenomenon connects every world with a magnetic field to its parent star through invisible threads of magnetism and charged particles, streams of stellar wind flowing between a star and its planets. The invisible particles following curved magnetic field lines that connect each world to its sun. This connection means that aurora displays are not just beautiful light shows, but visible proof of the magnetic bonds that tie planetary systems together. A distant star system with multiple planets, each world glowing with its own aurora displays as stellar wind particles follow magnetic field lines to create unique patterns of light on every world. Every aurora display, whether on Earth or on worlds we have never seen, represents the same fundamental dance between stellar energy, magnetic fields, and atmospheric particles that has been playing out across the universe for billions of years. This cosmic dance has been unfolding for billions of years, long before Earth formed, long before life began to stir in ancient oceans. A young Earth spinning slowly in space 4 billion years ago, its surface glowing red with volcanic activity. No atmosphere yet formed, the sun burning bright in the distance. The same solar wind that creates our aurora displays today once swept across a barren planet, laying the foundation for the magnetic field that would one day protect all life. Every breath you take exists because our planet learned to deflect the solar wind with invisible magnetic barriers. The aurora connects us to the deepest rhythms of the cosmos, streams of solar wind flowing outward from the sun in all directions, carrying charged particles past Mercury, Venus, Earth, and Mars, continuing toward the outer planets in an endless river of energy. When you see the northern lights dance across the sky, you witness the same process that shapes weather on Jupiter, creates the tail of every comet, and influences the birth of stars in distant nebulae. A comet traveling through space, its tail streaming behind it as solar wind pushes ice and dust particles away from the nucleus, creating a glowing trail millions of miles long. The solar wind touches everything in our solar system, connecting each world through invisible threads of magnetism and motion. Our aurora displays reveal Earth's place in this vast network of energy. The Earth floating in space with its magnetic field lines extending far into the darkness, creating a protective bubble around our blue and green world, deflecting streams of solar particles. The same magnetic field that guides compass needles also shapes the paths of charged particles from the sun, creating the curtains of light that have inspired humans for thousands of years. Green aurora curtains rippling across a dark polar sky, their light reflecting off snow-covered mountains and a frozen lake. Stars visible between the dancing ribbons of luminescence. In indigenous peoples watched these lights and understood they were witnessing something sacred, a connection between earth and sky that spoke of forces beyond human understanding. The aurora reminds us that our planet breathes with the rhythm of space, the sun's surface bubbling with magnetic activity, solar flares arcing high above the photosphere, sending bursts of charged particles racing toward the planets at millions of miles per hour. Every solar storm that creates spectacular aurora displays also demonstrates how our world responds to changes in our star. Aurora displays covering both polar regions of Earth simultaneously. The northern and southern lights creating mirror images of each other as charged particles follow magnetic field lines to both hemispheres. This planetary response to solar activity connects Earth's climate, weather patterns, and even the behavior of migrating animals to the 11-year heartbeat of our sun. The lights in our sky connect us to aurora displays on distant worlds we may never see. Jupiter's massive form floating in space, its poles glowing with constant aurora, displays far brighter than Earth's, powered by the planet's enormous magnetic field and volcanic moon Io. Saturn's aurora rings pulse with radio waves we can detect from Earth, while Uranus and Neptune create their own unique light shows in the darkness of the outer solar system. Saturn surrounded by its glowing rings, with aurora displays visible at both poles. The planet's magnetic field creating patterns of light that dance around the ring system. Every world with a magnetic field participates in this cosmic light show, each one adding its own voice to the symphony of charged particles and magnetic forces. The aurora teaches us that beauty emerges from the meeting of opposites. Solar wind particles streaming toward Earth's magnetic field, the invisible barrier deflecting most of the charged particles, while allowing some to spiral down toward the polar regions, creating pathways for light. Destruction becomes creation when solar particles that could harm life instead paint the sky with colors. Red aurora light glowing high in the atmosphere at 300 miles altitude, where oxygen atoms release photons after being struck by high-energy particles from the sun. The same forces that strip atmospheres from planets without magnetic magnetic fields become the source of Earth's most beautiful natural light display. As you drift toward sleep, imagine the aurora continuing its ancient dance above the polar regions, a peaceful Arctic landscape under a star-filled sky, green aurora curtains swaying gently across the darkness, their light casting a soft glow on snow-covered tundra and distant ice formations. The lights move in slow, hypnotic waves, following magnetic field lines that extend far into space, connecting our small world to the vast energy of our star. The aurora viewed from high above Earth, showing the complete oval of light that surrounds each polar region. The northern and southern lights creating perfect circles of luminescence on our spinning planet. This display continues whether we watch or sleep, a constant reminder that Earth participates in cosmic processes far larger than human experience. The aurora represents the gentle side of cosmic forces that could overwhelm our small world. Earth's magnetosphere extending far into space like a protective cocoon, its invisible boundaries deflecting harmful solar radiation while allowing beautiful light displays to form at the polar regions. Our magnetic field transforms potential destruction into wonder, turning the solar wind into a source of beauty that has inspired art, stories, and scientific discovery for centuries. A vast view of our solar system showing the sun at the center, with streams of solar wind flowing outward past all the planets, each world responding differently to this cosmic energy based on its magnetic field and atmosphere. Every aurora display reminds us that we live within a delicate balance of forces, protected by invisible shields that make life possible. The lights in our sky connect us to the birth and death of stars across the galaxy, a distant nebula glowing with the light of newly formed stars, their stellar winds creating aurora-like displays on planets orbiting within the colorful clouds of gas and dust. The same processes that create aurora displays on Earth occur around stars throughout the Milky Way. Each planetary system developing its own unique relationship between stellar energy and magnetic protection. An ancient star system where an old red giant creates gentle aurora displays on its remaining planets. The star's expanded atmosphere interacting with planetary magnetic fields in ways unknown in our younger solar system. The aurora phenomenon spans the entire history of the universe, from the first stars that formed magnetic planets to the distant future, when our own sun will create different kinds of light shows on the worlds that remain. Tonight, as aurora displays dance above the Arctic and Antarctic, they continue a story that began with the formation of our solar system and will continue long after human civilization has become part of Earth's geological record. A serene polar night with gentle green aurora curtains moving slowly across a star-filled sky, their reflection shimmering on the surface of a calm Arctic lake surrounded by snow-covered hills. The lights move with the patience of geological time, following magnetic field lines that have guided them for billions of years. The Milky Way galaxy slowly rotating in the darkness of space, billions of stars creating their own aurora displays on countless worlds. Each planetary system adding its voice to the cosmic symphony of light and magnetism. Every aurora display on every world represents the same fundamental harmony between stellar energy, magnetic fields, and atmospheric particles that connects all life to the stars. A peaceful view of Earth from space, showing the gentle glow of aurora displays at both poles. The planet spinning slowly beneath a canopy of stars. Our small blue world held safely within the vast darkness of the cosmos. The aurora reminds us that we are part of something infinitely larger than ourselves. Yet we are held and protected by forces that transform cosmic violence into gentle beauty. CTA like and subscribe card. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.